Welcome, everybody. We are going to skip a bunch of frames today. Let's do it. So today we have the most generous Sarade with us.
Hello.
And you'll notice it is not the usual welcome, but there is in fact an Excalidraw window open, which is just a drawing program. Would you like to describe what you're going to do today while I get Emacs set up in the background?
Sure. I mean, I suppose I can do this. Hold on.
Yeah.
I know to draw a lambda.
It's beautiful.
It's a bit off center, but all right. Oh, I forgot something. Hold on.
No difference.
So since we've been, or mostly you've been working on a network driver recently, we
Yes.
thought it might be a good idea to give a short introduction. Well, not so short, a basic introduction in how networking actually works in general.
Yes.
So, shall I start or should we wait a bit?
I think we're good to go. I'm just going to be working in the background here on this driver, trying to get transmission initialized in the same way as receive. But yeah, the code is yours.
All right. So when it comes to networking, there's a model that is typically used nowadays, which is the OSI model. And to get in a Shrek reference, the internet is basically just like an onion. It's a bunch of layers. And the way it works is we have 7 layers. I'm gonna draw that real quick.
Only 7?
Only 7.
Wow. Amateurs.
And even that's hard to draw apparently because I only managed to draw 6. So we have 7 layers. At the very bottom we have the physical layer. And we're going to be discussing not all of these, but the important ones in a second. Then we have the data link layer. Above that, the network layer. Above that, the transport layer. Above that, the session layer.
Naturally.
Then the presentation layer. And finally, the application layer.
Hey,
So before we start discussing these,
Indecent Labs says, Pog, I finally got on the stream. Yes, you did, Indecent. Welcome. You made it.
so we're discussing networking currently, and I'm going to draw a few lines here. So conceptually, this isn't perfectly well defined, but you could more or less draw a line here. And you could say that everything above that is user space. And everything below this is kernel space. That's not particularly well defined, and there's nothing in any standard or RFC, from what I can tell, that really makes this distinction. But conceptually and also in the real world, typically everything in the transport layer and below is implemented in the kernel as network drivers, and everything above that is in user space. And then there's a second line we can draw somewhere around here, right through the data link layer. And everything above that is software. And everything below that is hardware. Again, these lines are just conceptual, so that we have a basic understanding of what we're dealing with here. You will sometimes find that, as in the case for the E1000 chip that we're dealing with here, it has some hardware facilities to accelerate network and transport layer protocols. So Without further ado, let's get into the layers. So first of all, we have the physical layer. Okay.
That's
Uh,
me.
or actually, before that, just very quickly, just so you know, we're mostly going to be talking about the network and data link layer here because that's where the actual networking happens. The physical layer is typically implemented in hardware, so it's not that interesting. Transport layer is a bit too advanced right now. We can barely send packets. The session and presentation layer are generally fairly useless in my experience. I mean, there's some applications that actually use them, but if you're, for instance, writing a web server, then you don't really have anything on the session layer. You could perhaps argue that a TCP connection over which you send multiple requests is maybe a session, but even that's really just on the transport layer. So session and presentation layer aren't that useful in the general case, and a lot of the older TCP IP model combines both of them and the application layer into one layer. And finally, the application layer is actually what sends and processes the data. Anything below that is just concerned with transporting data. It doesn't actually care about what the data is or know anything about the data, or at least not much. So first we have the physical layer, and we're not really going to be talking about that much. So this is responsible for encoding a stream of bits as an analog signal. So on the physical layer, we're dealing with individual bits. So roughly speaking, we're taking some sequence of zeros and ones and transforming it into something that can actually be sent over a wire, because we can't really send ones and zeros over a wire.
Not yet.
As the name might suggest, the physical layer deals with things like how how do I encode a signal, how do I decode a signal, how do I prevent errors, and so on and so on. How to actually transmit something as an electromagnetic, but as an electromagnetic wave if we're talking about Wi-Fi, and things like for wired connections, typically either copper cables or fiber. And that's really all I have to say about the physical layer because, of course, there's a lot that goes into this. But this is mostly signal processing stuff that we're not really concerned here. And again, as I've mentioned, this is typically implemented in hardware. So, and that we're already done with the physical layer, basically. There isn't really much else to be said here that would be of any use to us right now. So, this next one is going to take significantly longer, and I'm going to use this nice green color for it, and that's the data link layer. That one we care a lot more about.
Yeah, that's the one where everything goes wrong.
That's where a lot of the magic happens, yes.
Yeah.
So, over the course of this discussion, we're basically going to answer a very fundamental question, and it's how does host A send data to host B, while either A and B are on the same network or on different networks? The
Just
data
connect
link
them with
layer
a
deals
cable.
with, come again?
Just connect them with a cable.
Basically, but it's a bit more complicated than that because there's different ways of connecting things with a cable.
Ah,
And there's different network topologies.
that's true. Like what wires are actually in the cable? What type of cable is it?
How they're connected, more or less. The type of cable, whether it's like copper or fiber, we don't really care about that here.
True, just
And
that
the
there
example
are.
is giving me an error constantly. The canvas seems to be too big. Fascinating. I wasn't getting this error earlier, so maybe if I just like you're also connected to this instance, but maybe if I
You can
just
yeet
throw you
me.
out real
Yeah,
quick, that might help. Stop session.
beautiful.
Maybe
I've been yeeted.
there.
I've
Maybe
also
that
yeeted
will help.
myself.
Maybe that will help. Otherwise, I might have to delete your
Done.
wonderful drawing further up. because it seems to be complaining about that a lot right now.
Feel free to delete it.
So I will
R.I.P.
quickly remove this, unfortunately. It's
You're a
worth noting that I
murderer.
wasn't getting any of these errors when I tested this out a few days back, so I don't know what it's on about, candidly. But anyway, we'll get back to this. Network topologies.
Gonna start
For
getting
instance,
floating
there's
point
the
errors.
so-called... Come again?
We're gonna start getting floating point errors because we're so far off to one side.
Did you like move to... No, this is on my screen though. I'm pretty close to the center. Anyway, uh, one possible topology, for instance, and this will, you'll see why this is relevant in a moment, is the so-called bus topology, where you have, at least conceptually, a central cable to which everything is connected. Another possible is something that's typically referred to as the star topology, as far as I know, and it's where everything is connected to some sort of central node. This node is typically called a switch, or sometimes a bridge. Now, uh, conceptually, this one here, the bus topology, is the better model. Conceptually, even though home networks are typically arranged in this star-like model, and I'll explain why. So, the way A sends a packet to B is in a fairly stupid manner, actually, because as you can see here, there is no direct connection between A and B. They're both connected to the same link. A link is conceptually like a local network connection is typically called a link. But there is no cable between A and B. And the reason why that's not typically not the case is because in a large network that would become unfeasible. If you connect all hosts together individually, that's a lot of cables,
N
right?
times M.
And n squared, even if you connect every host to every host.
Oh
And
god.
in a wireless network, for instance, there are no cables. So this is how it works. Everything is kind of, so long as it's within range of, as long as devices are within range of each other, they can send each other data. Now, what implications does that have for how we send data? Well, the only way A can really send data is it just takes the data and it throws it on the link. Since everyone's connected, everyone is going to get the data. And that's always the case when you send a packet on the local network. And that's why if you're connected to, for instance, a public Wi-Fi, you should be careful how and if you connect to your bank, because everyone who is on the same network could just be listening to what you're sending and seeing all your packets if it's not encrypted.
I'm sure they're just being nice and making sure everything gets through properly.
Definitely. Well, typically that's what you're supposed to do, and that leads very nicely to the next part. How do we actually send data to B and not to just everyone? Well, we can take inspiration from the real world here, specifically from mail. And I'm not talking about emails, I'm talking about good old-fashioned mail.
Chain ma- oh.
Regular mail that's actually sent physically, a letter. If you're sending a letter to someone, you don't just write the letter, put it in an envelope, and then throw the blank envelope into a post box. It's
That's
not going to work. I'm not going to know where to deliver it. So how does the postal service know where to deliver your letter?
an address.
You put an address, exactly. You put an address on it, and that's the same thing that we can do here. And these types of addresses are typically called MAC addresses. Or not typically, they are called MAC addresses. And MAC stands for media. No, that's not an M. Hold on. Media or medium access control. There's also like two other things that MAC can stand for, I believe, but in this context, it means medium access control. And as a side note, there's also something called the medium access control sublayer, because the link layer is sometimes divided into two sublayers we don't really care about that much. And that's the part of the NIC, for instance, that interfaces, hold on, interfaces with the so-called PHY, and the PHY is basically the chip that handles the physical layer. It's a
Bottom right
chip or a
warning.
circuit that implements the physical layer. And the max sublayer is the part of a NIC, for instance, that interfaces with this PHY. Now, so what is a MAC address? A MAC address is no, that's not, hold on, I can't write today. It seems it's a 6-byte
By the way, bottom right warning.
value. Oh, my bad. Hold on.
It's all good.
Maybe this.
That is
There we go.
beautiful. Yes.
A 6-byte value. I can do this, I suppose. That uniquely, and we'll get to how and why in a moment, identifies a device or a host, a router, anything else on the local network.
So if
Yes.
I've got a question from chat. If we run out of MAC addresses, will we make a larger one called Big MAC address?
We'll get to that point, to how MAC addresses are assigned. We'll get to that in a moment.
Perfect. Perfect.
But that's a good question. What happens if we run out of them? So an example of such a MAC address is typically written as the bytes are written in hexadecimal and separated by colons. So an example would be like, I don't know, 1, 2, 3, A, 4, 5, C, B, 1, E, 7, 8, or whatever. Is that 6? That's 6. Oh, and it's
Yes.
colons, not dots. So this would be an example MAC address.
Which is 6 hex numbers.
6 hex numbers. So what can we do with this thing? Well, what we can do is we can take our data that we want to send, and just as though it were a letter, we can put it in an envelope. And only we put the destination MAC address. This way we know where it's supposed to be sent to. Also, the source MAC address is nice in case they want to send anything back. And typically there's some other fields as well, which we don't care about at the moment. And this entire thing, these headers together with the data, are known as a frame. And there are standards for what these frames are supposed to look like. There's different standards for wireless and LAN transmissions, but for wire transmissions, the standard that's typically used is the IEEE 802.3 standard, also more commonly known as Ethernet. So Ethernet is the standard that describes what these frames look like. So what can we do with this? Well, if we get back to our network here, now I'm going to draw 3 hosts. Now we can take our packet, and if A wants to send data to B, it fills in B's MAC address, and then throws the packet on the link. Now, that doesn't change that everyone's going to receive it. But what happens is C, when it receives, is going to check the address. And it asks, is this my MAC address? No, it isn't. So we yeet the packet. We don't care about it. Meanwhile, B is going to receive it. It's going to do the same thing. It checks the address. Is this my address? Yes, it is. So we enqueue the packet into whatever our network stack is. I can't write the word queue apparently. Hold on. Why does it have 4 letters that are not pronounced? Seriously, English. What is this language doing sometimes?
Also in the bottom right, a little bit again. Perfect, perfect. By the way,
so this is how we conceptually send a packet on the local network. We fill in the destination MAC address and then we throw it on the network. Now, there are a few more things to consider here. What if we don't have a bus topology? What if instead we have a switch? Let's see, all of these are connected to a switch.
Lico13 says yeet packets is greater than dropped packets.
Yeah, we eat the packet, we drop the packet. There's drop packet is the more common term. We'll say that, but conceptually yeet works fairly well, I'd say. So what happens here? It's much the same thing, really. A sends the packet, though A is only connected to the switch, so the switch receives the packet. Now, switches as well as routers have custom firmware and even operating systems running on them that know how to deal with that. So the switch will check the packet. It sees, okay, it inspects the destination MAC address, and it will then forward it. If it knows B's address, it will just send it to B and to B only. If it doesn't know the MAC address, or if it doesn't recognize the MAC address, then what does it do?
Interesting. Probably just drops the packet.
Nope, that would be very bad.
Oh, because the switch can't. So it's got to basically just enumerate all of its connected devices, right? Am I crazy?
It doesn't really have a way of asking for MAC addresses. What
Interesting.
does it do if it just gets a packet? It doesn't know where to send it to exactly.
Is it a broadcast packet? Because it'd probably send it everywhere.
If it's a broadcast packet, it will send it everywhere, yes. But in this case, it's specifically addressed to B. It arrives at the switch, but the switch doesn't know what B is. It doesn't know B's address, or it doesn't recognize that the address belongs to B.
So
Because the way yes,
does it send a failure back to the source MAC address because it can't
no,
find the
because
desk?
picture this situation. You plug in D to the switch. The switch doesn't know what D is, but you know D's MAC address, and you want to send a packet to D. You can
I
do that. You can
see.
throw it and link it. Normally, conceptually, it's supposed to arrive. That's why I mentioned this is the better mental model. You can throw something on the link, you know it's going to arrive. So here, if you throw something on the link, it's know it's going to arrive if B is on the link. But how does it arrive there? It's a lot stupider than you might think. It's a very simple solution.
So does it literally, if it doesn't send it to everybody,
It does.
it
It sends it
does.
to every pod that it's connected to. It just sends it to everyone, and someone's gonna get it, hopefully.
So what if 3 people handle it and then like you get 3 acknowledgments that it's been handled sent back?
Well, that's not how this works because B, D, and C will inspect the packet, and the D and C will drop the packet because they'll see, okay, this is not my MAC address, and only B is going to reply.
Because the MAC address has to be unique on the local network.
Correct. Correct.
Ah, I'm getting it now.
So, and this is, by the way, how switches discover MAC addresses. They just listen to incoming traffic and they inspect the headers, and then they'll see, okay, at this port, and when I say port, I don't mean like TCP and UDP ports. I mean a switch has different ports that you can plug things into, these kinds of ports.
A
So you
cat
plug in
6.
something, and it just listens to packets coming from that port, and it inspects the source MAC address, and that way it knows, okay, this port is this MAC address, and that's how it eventually figures out who is where.
So it has like a lazy loading cache.
It has a cache, definitely, yes. It doesn't always forward everything to everyone, but it eventually learns the topology, if you will, of the network, who is where. But that way, if you unplug A and plug in E or something, and then you want to send a packet to E, well, the switch will then forward the packet. When it gets it back, it sees that, okay, suddenly I got a new MAC address, and probably the switch has also registered that there was a disconnect, so it's going to update it and so on. So the switch knows how to take care of that. But because of this, because the switch can still forward it to everyone, this is why I said that this is the better mental model. Because just the fact that you have a switch doesn't mean that B suddenly doesn't need to inspect the MAC address anymore. Just because you get a packet from the switch doesn't mean it's addressed to you. So you still need to inspect the address. So this sentiment of you throw it on the link and everyone gets it is still the better mental model, because that's what you need to check for always.
That
So,
is very cool. So like we're communicating right now
hmm
through the internet.
hmm
So you're saying that how do I get your MAC address even though you're not on my local network?
we're going to get to that on the network layer.
Okay. Okay.
We're not on
I'm
the same
jumping ahead.
network. That's not what the link layer is for.
We've got a
Link
question from
layer,
chat as well.
yes.
What's the port in lower level term?
What do you mean? You mean like a switch port or something?
Yes, I believe they're talking about the literal like ports you plug into.
That's literally just if you look at the switch or the router, there's like you can plug in cables there. Those are the ports, if you will.
The Ethernet plugs.
It's just where you plug in the cable. Yes, the socket, if you will.
Yeah. Is it used as like TCP port or UDP port?
No,
Ah,
that has nothing to do with those kinds of ports.
yeah, that's a software level port, which was
That's
made.
a software level concept. This is literally where you plug in the cable. Like, for instance, if you have on my router, there's four places in the back where I can plug in four cables at one time. So those four things will be considered ports then.
Yes.
This is a somewhat confusing thing about networking sometimes that we use the same terms to mean different things.
Between hardware and software very often.
Mm.
Because the software originally was made to mimic the hardware and then it grew out of that and now it's just weird
Yeah, well.
names.
Mhm.
So are those software ports just permanent memory allocations? Ports are
We'll get to ports later, to software ports.
yeah, I
That's
think
on
they're
the
an
transport
addressing.
layer. That's two layers up from where we currently are. So the data link layer doesn't know anything about ports on the TCP UDP level. It doesn't really know anything about ports to begin with. That's just the switch has to handle that because it has ports. A host doesn't really. It's just connected to a network.
So like your
Now,
router would have a buffer in memory permanently that refers to like those four ports and the MAC addresses at them
something like that, yes.
because it has its own cache.
Mhm.
But
And
that would
speaking of
be
routers, that's something worth mentioning that a router on your home router isn't just a router. It's a router and a switch and some other things as well. So the actual
modem.
if you connect two devices to your router and you send data between them, the actual part of the router that's transmitting the data is the switch. So that's just forwarding on the local network. So it's not just a router, it's a router and the switch as well.
Otherwise, you couldn't plug anything into it.
Yeah, otherwise you wouldn't be able to do much with it. Now, there's a few things we need to address about MAC addresses. So earlier we mentioned that MAC addresses are unique. And this is important. There's two questions that we need to answer here. How can we ensure that they're unique? And why do they have to be unique? Any ideas?
As far as the why, I would assume it's
Mhm.
because when you send something to someone, you don't want two people to get it.
That's a part of why we need them to be unique. Yes, that's one problem, but there is a much more glaring problem why that categorically simply must not happen. And the problem is that if two hosts have the same MAC address on the same network, they can't send each other anything.
Ah, the
That's the
consequence
main
of them having
problem.
the same one. Yeah.
Yeah, because everyone, either one is just going to think that it's for themselves. And
So
I'm not sure the switch would even forward if it sees that the destination and source are the same, if it even gets to the switch, because it would probably just be rerouted internally.
insanity. That makes a lot of
So yeah,
sense, though.
yeah. That's why two devices on the same network simply must not have the same address. Packet duplication, if you send it to two people, sure, that's also a problem. That wouldn't be good either. That would be enough of a problem to make sure that never happens. But this is the much more glaring problem that you simply would not be able to communicate.
That's
So that's
definitely
the why.
a big one.
So let's write this down. And you can think about the how for a second while I write this down.
Is it you? Oh, it's my Mac. Yeet. Okay. 12 bits is a weird amount of bits.
So, any ideas as to how we can ensure that MAC addresses are unique?
Hardware could have it like set that each one is unique, and then each time the switch gets a duplicate, it could just add one, and then it always does the same translation.
That's a bit complicated. What if we don't
Yes.
really have a switch and we connect them together? Uh, that's not really how it's typically done. You can there are ways of like setting your MAC address if you really want to. But typically, every device just has a MAC address. If you look at the like bottom of your router, there's typically a sticker with the MAC address on it.
Yes.
So physical devices have MAC addresses, and these are actually um, the way this works is that uh, NIC, router, and so on manufacturers they reserve MAC addresses.
So what if you have two devices from the same manufacturer on the same network?
MAC address ranges, more specifically. Let's write this down. MAC address ranges.
Ah,
And I think they're generally globally distributed by the IANA, I think. I'm not sure what the acronym stands for at the moment. I forgot that. And don't always remember that, but this is kind of one of the organizations that deals with assigning addresses and identifiers to everything. And I believe it's them that assign MAC addresses. So basically, if you want to manufacture routers, you can ask them, okay, I want some addresses, and then they'll give you an address range, and then every device you manufacture gets a unique address from that range. And this is how you can be sure that no two addresses or that no two devices have the same MAC address.
so the only way that no two devices have the same MAC address is because they're all made by like three companies and they talk to each other.
Basically, yeah.
Okay, that's not going to go wrong at any time.
Yeah, well, there are ways of like ameliorating this issue because it's true that you might run out of address space eventually or something like that. So there are ways of setting like virtual MAC addresses, if you will. I'm not sure what they're called exactly, but there are ways of configuring them. Or in the case of QEMU, you just have to pick one, basically, what we're doing right now.
But
And
there's like 256 to the power of 6 possible MAC
something
addresses.
like that, yeah, yeah.
So there's plenty.
There's enough. I mean, we are starting to run out of IP addresses, but those are arbitrarily those are only 32 bits, so it's a lot less bad with MAC addresses, but still. And the thing is also though that with MAC addresses is that they're only really valid on the local network, so collisions are already much less likely.
Right. And how many networks have more than even 200 devices connected?
Not a lot.
Yes.
Now, um, so there's one more question which we can't answer just yet, and that's we've kind of glossed over that. How does A know B's MAC address?
Ah.
We'll get back to this later. We'll get back to this later.
The
So,
mislead.
for now, there's another question I want to ask is what about other networks? So we know how to send stuff on the local network, but what about other networks? Like if I have my little network here with like a few hosts connected to each other, and then I have 30 other networks, and on the other side of the world, I want to connect to, I don't know, YouTube or something, or Twitch, which is probably somewhere else entirely. So how does that work? Because it's not just one huge network. They're different they are not just one huge network, they're different networks. And typically network boundaries end at routers, because I haven't discussed that yet. So a routers can forward things between networks, is how this generally works. And to discuss this in more detail, however, we need to move on to the next layer because this is where the job of the data link layer ends. It's only responsible for transmitting stuff on the local network. And if this discussion of the network of the data link layer seems rather short, that's because we've glossed over the entire part of the link layer that actually deals with interfacing with the physical layer. Because there's a lot more to that, but we don't have to implement that because that's typically implemented by the NIC. So we're not going to discuss that either. Like, there's a lot more stuff you could get into, but it's not really that important for us. So, where can I change my color though? Is it
It's
here? There we
yes.
go. We can, we're gonna switch to a nice blue for the network layer. So, layer number 3 is the network layer. And this is going to take a bit. This is a big one.
Could I give a small update on how the driver's going?
Still, go for it.
Okay. I have been hard at work initializing the transmission buffers. The nice thing is that the ring buffer of descriptors, transmit descriptors, you don't actually need to allocate buffers because I'm not sending anything. So there's no data to send, so there's nothing to allocate. So that's a huge step. That's way easier, less memory allocation. But yeah, we've actually got the ring buffer of descriptors all set up according to the documentation. And then I'm just now trying to actually set the control register to enable transmission. Then it will be as simple as writing one of these descriptors with an address for and length. And then we can just set the head to, or tail. We'll increment the tail, basically, and then the hardware will react and increment the head as it handles them.
Yeah, that's just a typical ring buffer, I see, yeah.
Yep, but it's going really well. We're nearly there. I'm just figuring out collision distance, whatever
I
that
see.
means.
If there are any questions in chat, by the way, just let me know because I can't see chat right now. I'm
Absolutely.
looking at too many screens.
There was one from earlier. Is this some UUID kind of thing? But I don't know what that is.
Basically, it's basically a unique identifier in a way. Yeah, MAC addresses are a bit like UUIDs. You can think of it that way.
And
In a way.
an
They are not.
IPv6 is very similar.
None of them really are UUIDs, but they
No.
function more or less like them, like addresses that are supposed to be different from one another, to put it simply.
Yes.
Right. So, we've already answered the question of how do we send data from A to B. But now we need to discuss how we do that on different networks, if A and B are on different networks. So, and fundamentally, the way this works is A basically needs to know, A or the routers that A sends the packets to needs to know where B is. Now, we already have an address. B already has an address. B has a MAC address. The question is, can we use the MAC address for this? What do you think?
Well, the MAC address, generally, it's only guaranteed to be unique per a local network. So,
Not really, because if manufacturers assign address ranges to them and they're unique, then they would also be unique globally.
that's true. So if each device already has its own MAC, then there's no, yeah.
So why? So what's the problem with using the MAC address?
It's not big enough. It's only 6 bytes.
No, that's not the problem. We are getting to something, but those are even shorter. So the MAC address length is not the issue.
That is a good point why you can't just use the MAC address. So even if two computers have the same network card in them, the MAC address will be different. because the manufacturer like increments by one each one they make.
So
I don't know. I don't
if
know.
we draw upon an analogy from the real world, if we're on the same, if say we're on the same street, then if I tell you that my house number is 37, you know where to find me. But you currently live in the States and I don't. So if I told you that my house number was 37, would you know where to find me?
Not at all. That's a good point.
Oh, really? Because the glaring
It could be
problem
anywhere.
is this doesn't work because
What street are you on? What
that
country? What?
too,
Yeah,
a
it's
MAC address doesn't tell us anything where B is. It doesn't tell us anything about where B is. So we need an address that can more or less tell us where and what network we can find B. Because the thing is, MAC addresses are unique to a network, not unique, are unique to devices. So even if two devices are on the same network, they can just have completely different MAC addresses. So the MAC address doesn't tell us anything about where a host is or what network they're in.
which means that it would have to like search the entire internet every time you make a
Yeah, which is
request.
not really that feasible. You
No,
can't really send if everyone would have you'd have to send a packet to everyone in the world, and that's not gonna happen.
exactly.
You can try, you're gonna crash very quickly if you do that. So we need something like a MAC address, but it needs to tell us what like where we can find it. And these addresses are IP addresses. IP in this case stands for Internet Protocol. Now, uh, to understand how the network layer works, we have to talk about IP addresses and we have to talk about them extensively. Because if you understand IP addresses, you more or less understand how networking works. Now, what is the layout of an IP address?
It's 4 bytes, and the first two are like vendor specific, is what I think.
No, they are 4 bytes. That's true. So an IP address
I was close.
is a 32-byte value or 4 octets. In networking, we like to use the term octets because some of these standards, the IP, the Internet Protocol, the RFC for that is from, I believe, 1971. And back then, bytes weren't really guaranteed to be 8 bits.
The 11-bit mainframes.
So this is why in networking, you'll rarely ever see the term byte and you'll always see octet because that just means 8 bits. I'm going to continue using bytes because that's simpler. So an example IP address would be something like 192.168.42.3, whatever. Now, the difference between a MAC address and the IP address and an IP address is that different parts of an IP address have different meanings. In the case of this address, for instance, this is the network prefix. And this part, not sure it really has a name. We can call this like the host part or something. And in this, if this is the network prefix and this is the host part, that means that if, or the network prefix identifies well, if it's called the network prefix, it identifies the network that a host is in. What can we follow from this? What follows from this? What does this mean?
uh, I would say that the host you can basically designate where to send it more efficiently instead of having to like broadcast it to everybody. And then
And
the
that's
go ahead.
yes.
And then the port is used to like define a MAC address or something.
Port is for multiplexing. That's later on. We'll get to that.
Okay.
But the main consequences of this is if two hosts have the same network prefix, then what? Then they're on the same network.
that does sound reasonable.
So, for instance, if we have some other address, I mean, up here we used 192.168, what did we do? 42, I believe. 42.3. If we have some other address, 192.168.42.7, then we know these two are on the same network. And we already know what to do if they're on the same network. We can send data directly. But we'll get to that a bit. We'll get more to that. So, the question is, how do we actually know what's the network prefix and what's the host part?
Of
So,
3 bytes
yes.
versus 1 byte.
Yes, but it's a bit more complicated than that. So, for a history lesson, this is how it used to be. It used to be the case that IP addresses or address ranges were divided into classes. We had class A addresses, and these were addresses from 10, starting at 10.0.0.1 up to I believe, well, before not 127, that one is special, but up to almost everything before 128. And then class B, I should probably delete this. And for class A addresses, the first byte was the network prefix. So for class B addresses, starting at 128, yeah, I believe it was just 128.0.0.1, I believe. The first 2 bytes were the network prefix, and class C, sorry, started at 192.0.0.1, and for these addresses, the first 3 bytes were the network prefix, and there were some more classes for multicasting after that, starting at 224, and addresses before 10 were reserved and whatever, but these are the addresses that were commonly used. So with this old scheme, you could very easily determine the network prefix just based on the value of the IP address, on how many ones you have at the start. So this is how it used to be, but the problem is that that's a bit inefficient. And the reason is that if you look at this, half of the address range is class A networks. And class A networks, because they have a network's prefix of 1 byte that can be what, like one, very few class A networks, but in a class A network there can be, I forgot what it was, but it's like 16 million or something hosts.
That should
Most
be, yeah.
networks don't have 16 million hosts. We'd rather have more networks, right?
Are you sure about that?
Pretty sure. So that's why this scheme was eventually abandoned. This, by the way, is called classful routing. Because addresses are divided into classes. And this was abandoned in favor of something that's called CIDR, which stands for classless. I can't spell today. Classless interdomain routing. And this is the scheme that's more commonly used today. In CIDR, what you do is, in addition to the IP address, say 192.168.0.1, you also specify explicitly how many bits of the address are part of the network prefix. That's typically annotated with a slash and then the number of bits. So you may have seen this before somewhere with an IP address slash a number. And that in this case means that the first 24 bits, meaning the first 3 bytes, are the network prefix. If instead we took the same address but specified 192.168.0.1/16, then only the first 2 bytes would be the network prefix. And by the way, this is in bits. This doesn't have to be a multiple of 8. You could also do like /15 or /23 or whatever. And then the first 15 or first 23 bits would be the network prefix. And an equivalent description of this is the so-called subnet mask. You may have heard of that before.
I have. It's always sounded very confusing and scary, and like I'll never understand it.
For instance, the subnet mask for /24 would be not 0, hold on. 255, what? 255, 255, 0. And basically the way it works, if you take the subnet mask and you AND it with the IP address, you get the network prefix. If you take the converse of the subnet mask and you AND that with the IP address, you get the host part. And that's how it works. That's why it's called the subnet mask, because it tells you what part of the address is the network, part is the prefix. And these two are equivalent. You can write /24 or you can specify the subnet mask. They are the same thing, basically. They're different ways of expressing the same thing.
So the subnet mask is actually just like some number in binary that masks the proper bits to get the host network versus not.
Exactly.
And the reason it's 255, 255, 255 so often is because 255 is OXFF, which is 8 bits.
That's 8
also.
ones. So,
Yep.
so in binary, it would be this. This would be the same thing, but in binary.
That makes more sense. And then when you AND it, of course, only the bits that are set will be retained. Okay. So this one question, the subnet mask, when you AND it with the IP, will you get the host or the sub, like the...
You get the network prefix.
Okay. So the subnet mask gets you the network prefix. And then the opposite of that would get you whatever isn't that.
And that you get the host.
Okay. Okay.
Because the way that this works is that you always have a number of ones at the beginning. It's always, this is the number of leading ones.
In the mask. Okay.
In the mask, yes. Not in the address, but yes, in the mask. You can't, for instance, have 254 in here. That's not how this works.
Unless this is the last.
Yeah, obviously it's the last part of the mask. Then you'd have, if you had 254, then that would be /23.
Which would be so cursed.
Yeah, but that's the thing. That's people sometimes do that. If you have a /16 network, you can, for instance, divide it into separate or into separate /16 or /18 networks.
Interesting.
So,
interesting.
With this information, how does A send data to B?
Oh, God.
Well, we have to assume A knows B's MAC address. B's IP address. Because you kind of have to know something about B to be able to send them something. If you don't know anything about your destination, you can't really send them anything. Like, you have to know something. So typically that's the IP address. Now, of course, you can get the IP address from the domain name using something like DNS. We'll get to all that. But for now, we assume A knows B's IP. So, there's two cases. One, A and B are on the same network. How do we know that? we compare B's IP to our own, or basically we AND both of them with our subnet mask. And if they're the same, then we know we're on the same network. Of course, the consequence of this is that every host on the same network has to have the same subnet mask. If you set two hosts on the same network up with different subnet masks, then yeah, that's a misconfiguration on your part as a network administrator. So if packets don't arrive, then that's your fault. Like there's nothing that the network layer can really do about that if you misconfigure it. Right. So if they're on the same network, then we know what to do. A just fills in B's MAC address and sends the data. And we know that because A and B's network prefix are the same. By the way, are there any questions in chat perhaps?
There are no questions as far as I know, no new ones.
All
One
right,
question
so
I have,
Mhm.
does A fill in B's MAC address or does like the switch do that?
A fills in B's MAC address. The switch doesn't know anything about IP. The switch is on the data link layer.
Okay. So
Or typically, at least, switches operate on the data link layer.
so the
And the data link layer
IP
doesn't know anything about that.
is part of what's sent between A and B. Like as the data in the sent.
Yes, basically, yeah. So I wasn't going to describe that right now. So what we do is, in the general case, we take our data. I mean, actually, I need to like, no, this is fine. Our data,
Yeah.
and we fill in the destination IP, and the source IP because we want people to be able to send stuff back to us.
And that's actually just for the software on the other side to see that and handle that. It's not
So
like the actual
I'll get
network
to it.
card or router or anything.
I'll get to it. I'll get to it.
Okay.
Just you wait. And there's
Okay.
some more headers in here. And this entire thing is known as an IP packet. And as a side note, the term packet most properly is only really used for IP. When we're talking about Ethernet, we are talking about Ethernet frames. The term packet, it's not entirely wrong to call them packets, but it's very unusual. For Ethernet, especially. For other protocols, you're also not supposed to call them packets, but for IP, for Ethernet, it's especially uncommon to call them packets. But it's not wrong. But typically, they're called frames. And what we do with this thing is we take this little packet and we throw it in an Ethernet packet. So now this entire IP packet is our data that we're sending in an Ethernet packet. We fill in the destination MAC address, and the source MAC address, and then A takes this thing and throws it on the link, and B is going to get it. It's going to look at the MAC address, determine that it's for it, and so on and so on. We already know how that works from the data link layer. Now,
Mr. Mugame says, I have to make a game in Java for my school computer science class. I'm going to cry. I have to use Swing.
my condolences. My condolences.
That's a Java F.
So we still need to figure in like here, again, there's one thing we're glossing over. How does A know B's MAC address? We'll get to that in a second. But first, what about the second case? What if they're not on the same network? Any guesses to what we would do in that case?
Isidore says, then it goes to the router, I guess?
It goes to the router, exactly. We don't know how to deal with this thing, so we still fill in the destination IP, source IP, we put the data in here. We take this entire thing, we throw it in an Ethernet packet, we fill in our source MAC, and we put in, well, the destination MAC address of the router.
Interesting. Okay.
How do we know what the router is? Well, that's standardized. Typically, the router is at whatever the network's prefix is .1. So if you have like the network prefix 192.168.178, then the routers are 192.168.178.1. Typically, .1 is the so-called default gateway. Meaning, if you don't know where to send it to, send it there. That's the default gateway. So we send it to that. The router gets it. And then the router, well, what is a router? A router is a very special kind of hardware. Routers typically even have their own operating systems that are separate, dedicated operating systems for routers. And the router knows where to send it because routers communicate with each other. They build up network topologies and graphs of where what networks are and so on, and they'll find a way to route the packet to where it's supposed to go based on the network prefix and based on more information that they get from surrounding networks. So routers will be able to just generally push the packet into the direction of the network that it's supposed to go in. And once it arrives at that network's router, well, it will know where B is and send it to B. And we're not going to go into any more detail on the router level because that's
Rabbit
not
hole.
a complicated thing that really doesn't concern us. But basically, you can just hand the packet to the router and they'll know how to forward it.
Mr. Mugume says, can't you also set that in your network settings? But I'm not sure what he's talking about.
You can set what router you want to send it to, yes. So you may be connected to different routers, and you might perhaps even know if the host itself has routing tables. It might perhaps know that okay, that this router knows how to forward it to this specific network, so I'm going to send it to this router. But in general, if you don't know where it goes to, you send it to the default gateway. But yes, you can have more than one router.
Interesting.
So, so we know how to send stuff uh, through over the internet, and also if B wants to send something back, well, we fill in our source IP. So B can just fill in our source IP and send stuff back. Eventually, it's going to get to our router. It will fill in our MAC address, throw it at the link, we're going to get it. So what about that first case, though? Given B's IP, how do we determine B's MAC address? Any guesses as to how we might be able to do that?
I can tell you how it's not. I don't think that an IP address maps to like a MAC address through some formula, like mathematical formula. I
No.
think that you have to like basically ask.
You ask them. And the protocol for this is called ARP, or the Address Resolution Protocol.
That makes sense.
And okay, it goes on. So basically, what A does if it wants to know B's MAC given B's IP, it constructs an ARP packet. The exact format of it isn't really that important right now. And it basically asks who is B. Or actually, the format, let's go over the format because that's actually, it is important. So what we put in this packet is, so we fill in the source MAC address. That's easy, that's ours. We fill in the source IP, that's ours. We fill in the destination IP, not exactly in that order, by the way. But what do we put for the destination MAC address? Because that's what we're trying to figure out. What do we put here?
Isidiush asks, is it always broadcasted?
We'll get to that.
The
If you're talking about
destination,
app, we'll get to that.
yeah, the
So what do
destination
we,
MAC address is probably, since we don't know where to send it, it's either going to be like 0 to be filled in later, or it's going to be handled by like sending it directly to the router or the switch.
well, if you send it directly to the router is going to think it's addressed for them.
Interesting. So I don't
Or
know. I
rather,
would guess zeros.
yeah, the convention is you just fill in zeros.
Nice,
And
nice.
it's important to note that this is the ARP packet. This is not the Ethernet packet. This entire packet goes in an Ethernet packet. And what do we put in here? Well, for our source MAC, easy. We put in our MAC. What do we put in here for the destination MAC?
That's going to be the router.
No.
No?
We'd only be sending it to the router if we did that. And again, this is sort of link layer stuff here. So uh, we're dealing with addresses on the link layer. So what do we put in here? It's not the router's MAC.
It's got to be zeros again if we don't know.
Well, close. You could that's a matter of definition. You have to put in something, and we actually do the opposite. We put in all ones, or the MAC address is FF, 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 and this MAC address has a special meaning. This is the broadcast address.
Interesting. So one of them you set to 0 and the other of them you set to all ones?
Yeah, this is just in the app packet that's 0 because you don't know what to put there. But this address is well defined. This is the broadcast MAC address. If you want to send something to everyone with a link, you put in this address as the destination. Mind you
Interesting.
that this only works on the local network because routers don't forward Ethernet broadcasts.
So you can only broadcast to your own local network.
Using Ethernet, and you can only broadcast to your local network, yes, because we're on the link layer. That's only for the local network. So what happens is this gets sent to everyone. Even if you have like a switch, this just gets sent to everyone. Because it's a broadcast, right? Everyone's going to get it. Now,
Yes.
I will do something similar to what we did earlier with determining is this packet for us or not. So C is going to get the packet. It will inspect the destination IP, and it will check, is this my IP? No. So what do? We eat the packet again, right? But B is going to get it, and it's going to inspect the packet and ask, is this my IP? And yes, it is my IP. So what do is we take the R packet, and we basically, hold on, this is a bad drawing. One sec. For the source IP, this time we fill in, for the source MAC, we fill in our MAC address. And then the destination MAC, well, we know that because the sender A included its MAC address in the packet, and that way we know what to send it to. We send it back to A. And then the IP addresses are the same as before. This is a rather janky drawing, but it works. And then B is going to throw this back on the link address to A. A is going to get it. And what A does is it goes to its ARP cache and it makes an entry there. And this is basically a map from IP to MAC address. And it's going to see, okay, B's IP, and it's going to record that that maps to whatever B's MAC address is. And then the next time when it wants to send a packet to B, it can look up B's MAC address in the cache, and it will fill in the address and send it to B. And this is roughly how ARP works. So, to recap a bit, because we just went over a lot of stuff,
Yes.
the data link layer is responsible for transmitting data on the local network. We can indicate that data is meant for a specific host on the network by filling in their MAC address in the Ethernet packet. We can get that if we don't know their MAC address, we can get it from their IP address by simply asking them, and we do that using ARP. We broadcast an ARP who is request, and that goes to everyone, and then only B will answer with its MAC address. And you can actually use ARP for more things. For instance, if your IP address changes, you can send out an ARP request to yourself, basically. And that will tell everyone, okay, I have this address. This is called gratuitous ARP sometimes, where if a host receives an ARP packet, even if it's not addressed to it, it will still look at, okay, what's the source IP and MAC, and it will add that to its cache. That way you can avoid having to make too many ARP requests. And there's also something called an ARP scan, which is if you want to know who is on the local network, you just go through all the IPs that are part of the local network. You know what IPs those are based on the subnet mask or the length of the network prefix, and you just ask for every IP. You ask, okay, who has this IP, and you'll see who answers. So that's one way to find out what devices there are on the local network. On the other hand, if you want to send something between networks, well, that's what the network layer is for. And on the network layer, we simply fill in the MAC address of the router, send it to the router, and the router knows where to forward it. So basically, the way this looks like is it just gets to, this is often drawn like so. If we have the network layer here, so this is layer 3, this is layer 2, and basically packets just move in and out the network and Ethernet layer. So a router sends it to the next router, it receives it, determines, okay, who is this for, what router do I send this to, and so on. And it just goes up and down, back and forth between those two layers until eventually it gets to the router that actually is authoritative for whatever network the host that I'm trying to send this packet to is in, and then that router will send it to the host that I want to send it to. So, are there any questions about these two layers? Because we're mostly done with them now.
Oh, there's a question in chat. What's the size of a packet, or how large can data be before it's broken down into another packet?
That's a good question. That depends on the layer. So, very fundamentally, on Ethernet, the limit is, I believe, 1508 bytes. So, 8 bytes is the header, I think, if I recall correctly, and 1500 bytes of data. That's the hard limit on Ethernet. There's something called jumbo frames where there are extensions to the standard that support larger frames, but in general, an Ethernet packet is 1500 bytes of data. An IP packet can hold up to 64 kilobytes. How does that work? Well, if an IP packet is too large, if it's larger than the so-called MTU, the maximum transmission unit of a layer or network, then it has to be broken up. So there's a way of doing that. It's called IP fragmentation. I'm not going to get into that yet, but there is a way of breaking a single IP packet into multiple small IP packets in such a way that they can then be stitched together by the receiver and in the right order and everything. So that's generally how that works. Any
So
more
that's what
questions?
MTU means on my router settings. Zaria says, I have a Networks 1 exam tomorrow. Coincidence?
Oh.
Pog. It's not a coincidence. I actually keep track of your schedule, Zaria, so I'm just helping you out.
So if there are no more questions, we're going to talk about the transport layer real quick. And this is going to be just a short introduction because there's not much. It's the protocols here are similarly, if not somewhat more complicated at times than on the previous two layers. But in general, there's not so much to understand here. Like you don't have to know how, for instance, TCP works internally to know what it does. Whereas with IP addresses, you sort of have to know what is an IP address, what is the layout of an address, what do the different parts mean to be able to understand how they're actually used in routing. So, what is the transport layer for? Because we just discussed, okay, the physical layer, it transforms data between digital and analog signals. The data link layer transmits stuff on the local network. The network layer is for routing packets between networks. So what is that? If we can already route things between packets, we can already send stuff from A to B. So what do we need a transport layer for?
Security. Armored
Security is
transport in military.
security. You could say that that's on the transport layer too, the SSL, for instance, or TLS, but it's not the primary purpose, I'd say, of just the transport layer. You
Okay.
can put that on top of the transport layer, sure.
It's part of it, but it's not the point.
Yeah, what is the main like thing that the transport layer does?
I don't actually know, but I'm going to guess that it helps route IPs and stuff on the router. I don't
No, the
know.
transport layer has nothing to do with routing.
Is it so? Does the TCP like header go within an Ethernet frame?
No, a TCP packet goes inside an IP packet.
And the IP packet goes in the Ethernet frame.
Hmm.
Okay, I'm getting it now. So then the transport layer, you said we're running out of IPs. Does that have anything to do with that?
Not really.
Okay,
Sort of with ports, but not primarily, no.
interesting. Then I've got nothing.
Hmm. Um, Basically, the transport layer, and it's a bit hard to define, honestly, but it deals with, well, I need to resize this. It deals with, in a way, how data is transmitted.
Is that an H?
That is supposed to be a H, yes.
Just checking.
And I'm not talking routed, I'm talking about transmitted. So this deals with things like establishing connections.
Handshake.
That's part of it.
I'm
With
remembering now.
reliability, with packet loss, and so on and so on. Because networks aren't always well behaved, especially in wireless networks. Packets may just get dropped randomly, or if the connection isn't that stable. That just sort of happens. And how do we deal with that? Well, the easiest way of dealing with that is not at all. And that's where UDP comes in. UDP is the user datagram protocol. UDP goes back to around 1980. So it's an old protocol. And UDP is characterized as, oh God, you're doing, if you want to do CSE32 calculations for Ethernet, there's an assembly instruction for that does that on x86-64. There's the CSE32 instruction that does that. You do not want to do this by hand, ever.
So, okay, that makes
We
sense.
can discuss this a bit later, maybe. Right now I'm
That's
discussing
perfect.
this,
Yeah.
but there is a very simple way of I can give you some code for computing CSE32C, which is what you need for Ethernet.
Yeah, I was just thinking about if we actually want to try and send a frame,
You
we're
need the
going to need.
checksum for that. That's true. Um, I believe the NIC can do that though. I'm pretty sure
Oh,
it should be able
Pog.
to put the checksum too. Otherwise, we could do it manually, but typically you don't want to do that. And if you do, there is a specific instruction just for that on x86-64 to make that easier. Anyway, just because I'm looking at your screen and I'm seeing that you're doing this.
Yes.
Chat and seeing this, but I can actually see what you're doing on your screen. So, UDP is characterized as an unreliable, message-oriented, connectionless protocol with very low overhead because it doesn't really do much. In fact, it does barely anything at all. This UDP header looks like this. It has a source port, and we'll get to that in a second, a destination port, a length, and a checksum. And these fields are 2 bytes each, so in total that's 8 bytes. And the checksum really isn't anything fancy. It's just a parity check. So it's not a particularly useful checksum to begin with. The length is how much data I have, so the data is here.
It's more useful for hardware, the parity.
Since this is a 2-byte value, the maximum theoretical size of a UDP packet is 64 kilobytes. It's a bit less than that because you also have to factor in the IP header and UDP header. So what are ports now? Well, ports are basically a way of multiplexing or demultiplexing. I honestly never know which is which. In this case, I'm pretty sure it's multiplexing. Multiple connections to one IP address. Because if you could only really ever send packets from one IP to one IP, that's kind of limiting. We may perhaps want to connect to the same address from 2 different processes at the same time. And it's kind of annoying if you can only do that for one process at a time. So what ports do is, I should write that down. Maybe ports are a way of
That makes so much
multiplexing,
sense.
not really connections, but in general just incoming traffic. So what you'll do is, for instance, you can in the UDP header, you fill in the source port, which is, since it's 2 bytes, it's a 16-bit number. And then you put that packet in an IP packet. You put the IP packet in an Ethernet packet, send it to whatever it's supposed to be sent to. And then when you receive a response, it will be addressed to your port. That way, 2 services or processes or whatever that are running on the same host can send data using different source ports, and then the network stack knows that when it receives a packet addressed to its IP address, it can check the port to see what process it wants to send it actually is supposed to route it to. So this is what ports are for. And ports, because of this, only exist on the transport layer. Routers don't care about ports, and Ethernet doesn't care about ports. It's the ports only exist inside the network stack on the transport layer. And this is another thing that the transport layer is for it's multiplexing. And typically port 0 typically is supposed to represent any port, and that's typically if you create a socket, you fill in 0. That means you don't care about port, you just want some port. And ports 1 to 1024 are typically reserved on Linux for the super user. So you have to be root on Linux to be able to open a socket to any of these ports, and on Windows as well, I believe.
Which makes sense.
And there are well-defined ports, and that's what it's actually called, I believe, well-defined ports.
Is that 440?
In that range.
83.
For instance, 443 is for what?
I was going to 83. I think that's FTP. somewhere
Oh,
around
I
there.
don't know about FTP. That could be the case. Honestly, I don't know. But this is for HTTPS, for instance. 80 is for HTTP. 22, I believe, would be for SSH. And there are some more ports. There are also well-defined ports in the higher range. For instance, I believe it's what? To 25,536 or whatever, I believe is Minecraft.
Well
Minecraft servers are
defined.
typically on this port. Or it's some port that starts with 2500, I don't remember. It's some port. So you could have a HTTPS, HTTPS server, HTTP server, an SSH connection, and a Minecraft client connected to the same host, to the same IP, using all these different these different ports.
So the transport layer allows a single host to basically have its own internal software network where all of them are using the one network of the host to go through.
Essentially, yeah, that's one of the things it does.
Like each of
And
the, yes.
yes, with UDP, that might very well be the only thing it really does. Let's be honest, because UDP doesn't do much. If a packet is lost, it's just, yeah, it's
It's
lost.
gone.
UDP. It's because of that, it's very low overhead. Now, there's only really two protocols that are common on the transport layer. There's lots more, but there's only two that are universally supported. The other one, you probably know the other one.
What, a port that's universally supported?
The other protocol. One protocol is UDP, the other one is
Ah, TCP.
TCP, which stands for.
Transport Connection Protocol.
Not exactly. It's Transmission Control Protocol.
I was close. So what, how does it control the transmission?
We'll get to that. Also, as a side note, because UDP is called the User Datagram Protocol, a datagram
Is that just like a fixed buffer?
is basically just a message, if you will, a it's not really called packet. It's something like that. A fixed size, a message that actually has that is delimited. Basically, this is the size of this thing. And UDP packets more properly are called datagrams and not packets, because again, packet is reserved for the IP layer, so you should actually be calling them datagrams. I'm saying should because a lot of people just say UDP packet, and for UDP that's a lot more common than for say Ethernet. Ethernet, typically we say Ethernet frames, but for UDP it's perfectly fine if you want to call them packets. Just know that you're technically supposed to call them datagrams.
Isidiush has a question. Don't they fight? Like, hey, I want to go first. I'm not sure what that refers to.
I'm not sure what that refers to either.
Maybe like UDP, all the different ports.
Yeah, well, if you try to open a socket on a port that someone else already has a socket, the operating system is not going to let you do that. It's going to say, well, error, port is already in use.
So there can only ever be one port, one user of each port.
Exactly. Yeah.
Okay.
So for instance, you can't run two web servers on port 80 on the same system. That doesn't quite work.
Isidiush says packets on ports. I think I can handle that one. So each port can send or receive packets in any order. I don't think the order of packets is guaranteed, right?
Oh, it is not. They can receive in any order, especially since packets may not always be routed the same. To avoid congestion, what a router may do is it may decide, okay, it has two paths to the destination, and it sends some of the packets one way, some of the packets the other way, and they may arrive out of order. That's also the thing with UDP. It's unreliable, and in order transmission is not guaranteed. If you send two UDP packets, you can receive them in any order. Or also not at all, actually. They can just get lost on the way.
So in UDP, you would require like an acknowledge back and then wait for that. And then
And
you can send another one. And then,
yeah,
okay.
and because you don't want to implement that yourself, this is why we have TCP. TCP is even older than UDP. It's from 1974. And originally, TCP and IP were designed to be this monolithic protocol, the network protocol. But later they realized that that's a bit too big, so they split it up into two. And this stack is typically called, or was often called TCP/IP. You may have heard that before. And that's the traditional network stack. That's, for instance, HTTP or web servers work over TCP. Now, TCP is pretty much the exact opposite of UDP. It's a reliable, connection-oriented, and this is an important part, byte stream. And this is important that, oh, I'm gonna keep writing these everywhere. There is no such thing as a TCP packet. That doesn't exist. There is no TCP packet. You can't say A sends B a TCP packet because TCP is not message oriented. It's a byte stream. You can write 800 bytes into the connection and B will receive them in order. And if something gets lost, TCP will make sure to resend the bytes in order.
Oh,
So
wow.
there are no T. You can't send a TCP packet to someone. You can only write bytes into the connection, and you know that they're going to come out the same order you put them in on the other side. Now, of course, for transmission reasons, because you can't just send individual bytes, there is such a thing as TCP segments. And if people are talking about TCP packets, they typically mean TCP segments. And you can almost think of this as an implementation detail.
Yeah, yeah, yeah.
That's not to say that they aren't well defined. They are, they're very well defined, but it means they're necessary to be able to transmit data efficiently, but they're not in any way, shape, or form visible to applications that actually use TCP. Which means TCP is pretty much an abstraction over this entire concept of packets and segments. TCP just provides you with a duplex connection. You can send data to it, you can receive data from it. You don't have to worry about packets getting lost or things arriving out of order. It just works, basically. The only downside is TCP has quite the considerable protocol overhead, both in terms of size on the network, because a TCP packet is a lot larger. The typical TCP header is, what was it? I don't remember. It was like 32 or 64 bytes, more or less, and it has options you can set. Uh, or I shouldn't call it TCP packet, instead of saying TCP segment. And TCP is also a fairly complicated state machine. So the computational side in the protocol stack is also much more complicated, and it has this entire three-way handshake that you mentioned earlier, where if I
Yes.
want to a server, for instance, client to server, so this is the TCP handshake. The client sends a so-called SYN request to the server. SYN stands for synchronize, and I'm not going to go into the details of TCP, but basically it's a request to synchronize the sequence numbers, which refer to how many bytes have been sent, more or less. We can discuss them if you want to. We can discuss this into more detail, but I'd suggest maybe waiting until we've implemented everything below that. But the server sends back an acknowledgement for the client SYN as well as its own SYN. And because these are all flags, the ACK and the SYN fit in the same packet. And then the client sends back an ACK for the server SYN. And that's how you get this three-way handshake. That's why it's three packets. It's really client sends a SYN, server sends an ACK, server sends a SYN, client sends an ACK. So it's really four things that are transmitted. It just happens that two of them fit in one packet. So that's how you get this three-way handshake.
So if I were to turn that into a sentence, Like the client asks, hey, can I connect? The server responds, yes, can you do this for me? And then the client does the thing for them.
Yeah.
Okay, okay. I'm just making sure. So it's like the middle two, you could break it up and say, yes, you are allowed to connect. And then another sentence that says like, can you do this
Yes.
thing for me? But you're saying, yes, can you do this thing for me?
Yeah, it's basically perhaps a bit clearer. It's if I say the client asks, server, are you there? The server answers, I'm there. Are you there? And the client answers, yes, I'm there. Basically like that. Or did you actually, yes, I'm here. Did you receive that? Yes, I did. Something like that. So that both sides know that they've actually been successful in sending data to each other.
King
And this,
buns.
yes, they can be sent in different packets theoretically, but I'm not sure that's well defined in the standard. I think they're actually required to be in the same, but I'm not exactly sure about that. I'd have to look that one up. But there's no real reason to break them up. No reason whatsoever, actually.
That makes sense. King Bun says, ugh, not the three-way handshake. And he got stopped by Automat. Zarya says, why three-way, not two?
Well, it doesn't really work because the client sends a message which the server needs to acknowledge. But then the server also wants to know that the client is really there, so it sends a message back, which then the client has to acknowledge. Basically, to describe why this is necessary is because both the client and server have different sequence numbers and they need to synchronize them. And to explain this into more detail would require explaining how TCP works internally. But basically, there are two numbers that are used to control transmissions back and forth because TCP is a duplex connection. It goes in both directions. The client can send to the server, and the server can send stuff back. So they both have sequence numbers that track how many bytes have been sent. And because the bytes that the client sends to the server are independent of the bytes that the server sends back, you have two different sequence numbers for that. And this exchange is basically the client and the server telling each other their sequence numbers. It's a bit more complicated than that, but that's how it works, basically.
So let's say there's like some internal state, and they basically need to synchronize their internal state.
Yes,
Okay.
basically.
Zarya says, so sequential, no. I don't know what that means. Act no, seek no, act no, sec no.
Sec no is sequence number, yes.
Ah, yes, that makes sense. So he's saying sequence number is sent, and then we get an ACK,
Yeah.
and then,
Seek
yeah.
or sequence number is how it's typically abbreviated. Seek or seek no, however when you pronounce it. And well, typically these are the two protocols that are supported everywhere, TCP and UDP. Everyone supports TCP and UDP. Even routers from 20 years ago support TCP and UDP. And because there are still routers from 20 years ago everywhere, you're basically never going to get a new transport protocol, at least not in the foreseeable future. Because the only thing that is guaranteed to work everywhere, and I mean everywhere, are TCP and UDP. So, which happens a lot more often is that protocols are built on top of UDP. If you want to make a new transport protocol, you build it on top of UDP because UDP is a very lightweight protocol.
It has the least overhead. So
It's least
adding on
overhead.
top of it makes sense.
Yes. And a good example of that is one that's fairly new, actually. It's Quick, which is a transport protocol that HTTP 3 uses. HTTP 2 and 1 use TCP. But HTTP 3 uses a new protocol called Quick, which is built on top of UDP, and which basically it's an attempt to solve some of the problems that TCP suffers from, especially in regards to how web traffic works. I'm not gonna get into that in any more detail unless you really want me to, but
We're good. We're good.
I have to just say that building stuff on top of UDP is a fairly common solution, and you could then very well call Quick a transport layer protocol. Whether you want to put this in the transport layer or above or application layer is, I'm not sure
It's a
if
little
it's too
messy.
well defined. It's really just a question of semantics, really. And for instance, because it's lightweight, UDP is very often used in contexts where you don't really care that much about reliability and you care more about speed. A very good example is what we're doing right now, live streaming. If you drop a few frames, then you'd rather receive the new frames than try to keep up or catch up with the old frames.
So we've actually skipped 379 frames. Like,
Apparently, yeah.
yep.
And we just don't care. We just move on with our day. Because if we try to start catching up, we'll always lag behind forever. That's why in audio transmission, video transmission, also if you're connecting to, if you're playing a game, you're connecting to a server, those games often use UDP for that. I believe Minecraft uses TCP though, but still. UDP is a common choice for that when you don't need the reliability or you just don't need the like everything that TCP gives you. And sometimes TCP, at least in my experience, can be a bit annoying to deal with because sometimes you simply want messages. You don't really want a byte stream. And you don't want to deal with receiving half a message and then waiting for the rest or something. So sometimes you might want a datagram or message-oriented protocol. Though, of course, you can always build that on top of UDP, and that's basically what HTTP is. And are there any more questions about the transport layer or anything below that have come up in the meantime? Because otherwise, we're basically done with this now, with the
There
transport layer.
there was an overwhelming it makes sense a few minutes ago,
Hmm.
but Mr. Mugume guessed ahead, I think. Oh, for streaming HTTP requests, so that's yes. And then, King Buns asked about the TCP implementation. Do they use the sequence numbers to break the pure byte data up in messages from each party?
Uh, not well. That's not really a question that. That's not really how it works because the sequence number is how many bytes you've sent. So if you send
Okay.
1500 bytes, you increment the sequence number by 1500.
And then if you only receive 700, there's 800 left over.
Yeah, basically. So then if the server receives the on the other end they receive 700, well when they won't receive half a second, but then they can acknowledge the next, you can also just acknowledge 700 bytes and they'll send back the 800 that's missing or whatever. Um, but yeah, the sequence number is how many bytes you've sent. And it's important that it's bytes. It's not packets or anything. There are no packets, it's bytes. It's a byte stream.
Nice. King Bun says, okay, that is what I was meaning to ask. Awesome. Like, it's a way of dividing their time across the channel and knowing how it... data, not time. It's a way of dividing their data across the channel and knowing how it should be structured.
Sort of, yes.
Yeah.
TCP is a bit of a complicated one. It's not as easy to describe as UDP. There's a lot of internal state with it. You can read the RFC. I believe it's RFC. What was it, like 731 or something? What's the TCP RFC? The like 793. So RFC.
That's like the technical spec, right?
Yeah, it's RFC stands for request for comments.
So it's basically just like a paper that says, hey, make fun of
Yeah,
me.
it's a paper. That's the best way to think about it. It's not necessarily a standard. A TCP, an RFC can become an internet standard, but it's mostly just a way of formally specifying something, more or less. That doesn't mean it's binding, though, and RFCs can get superseded or made obsolescent by new ops. That happens all the time. For instance, HTTP is actually an older. How old do you think HTTP is? Do you happen to know that?
I think it's older than TCP. It's just like one of those things.
No, not really.
Then I have no clue.
HTTP is, if I'm going to Google this to make sure I'm right, but I'm pretty sure I am about this one. Yeah, HTTP is from the earliest version is from 18, not 18, good God, 18, 1989, Do you happen to know who invented HTTP? He's a very famous person,
It
sometimes
wasn't
called the.
Donald Knuth, was it?
No, it wasn't Donald Knuth. He's sometimes called the father of the internet. This guy.
John McAfee?
No, it's Tim Berners-Lee.
Hey, King Buns guessed it.
Tim Berners-Lee, very famous name. He invented not only HTTP but also HTML. Well,
Ah,
or rather HTML to be used to display websites. So he is generally credited to be the inventor.
Mr. Mukame and I
World
feel the
Wide
same
Web,
way.
or the man who invented the internet, basically. Networks had been around since far longer than that, but he's kind of the one who came up with HTTP as a way to easily uh, transfer data in the form of websites, and that was basically the start of the internet in the early 90s.
King Bun says hypertext misery language.
Yeah, the hypertext transfer protocol and the hypertext markup language.
Isidius says, but I am sure I did. He created the internet.
This leads very nicely to actually, we're skipping the session and presentation layer because
That's
that
fine.
don't matter. We're getting to the application layer. And this is going to be a very short summary because we've already been discussing it now. The application layer actually processes the data. Because in case you have noticed it, everything we've discussed so far doesn't actually care about what data it's transmitting. It's just transmitting data. The link layer knows where to send the data. The physical layer knows how to encode it. The network layer knows how to route it. The transport layer knows how to make sure that it arrives if that's what you want. But those layers don't care about what you're actually sending. At least not. There are some flags you can set here and there, and for like IP to like kind of give hints to the router of what this might be. Like maybe I want this to be, maybe this is like a stream and I don't care if this gets lost, I just want it to be sent quickly and so on. But in general, those layers don't care about what they're sending. The application layer is what actually produces the data that gets sent and processes the data that it receives. So this is your web server is the application layer, or anything you write that actually opens a socket and sends data to it. And that's really most of what there is. We've already discussed HTTP, for instance, is a very common application layer protocol. If in case you don't know what a HTTP request looks like, HTTP request is just text. And if you want to, for instance, get Google's homepage, you can just send the GET request for this path / is the root. Then you need to tell it what protocol you're using. It's use HTTP 1.1. You can then, and these lines end with a card return line feed. And then you can specify
Naturally.
some headers like the host is I want this to be sent to www.google.com. And this, by the way, is just an annotation so that it's required by the HTTP 1.1 standard, but this is just so that the server really knows that it's intended for them as like a second check. This has nothing to do with how it's routed or anything. And then we put another CRLF at the end. We take this entire thing, we throw this entire thing, this is a HTTP packet. We put this in a TCP packet, or TCP segment rather, or not, it may also be split across several TCP segments if it's large, but let's say it's in one. And then this entire thing, which is in the TCP segment, eventually goes into an IP packet. And then this entire thing, I'm not going to draw everything again, but this IP packet, it gets put into an Ethernet frame. And then that gets sent to the wire. And that's in the same manner you get an Ethernet frame back. You extract the IP packet, you check, okay, is it really for me? You extract the TCP packet, you see, okay, what port does this go to? Okay, it's me. The kernel then routes the packet to you, and you don't even get the TCP packet segment. You just get the HTTP data. You can then read the data from the connection, and that's your response. So this is how you connect to a web server, roughly speaking. And this is mostly how networking works. There's a few more things that I want to go into because um, there's two things related to IP addresses that we've kind of glossed over. And that's how
Silly the name
does
is.
a nobody's IP address. So if A wants to send data to B, how do we know B's IP address?
Because we talked about ARP, but that's just how to resolve a MAC
That's
address
how we get
from an
MAC
IP
address.
address.
Know the IP. How do we even know the IP?
Well, how do we even know that there are IPs or like that things exist? You have to be
Oh yeah, of
contacted.
course. This is kind of a chicken and the egg problem. Like we need to know at least something to be able to get everything else. That's
Right.
true. Um, so typically, yes,
Ah,
a simple way is you hard code it.
you just know the IP address of the
You just know
recipient.
the IP. You just say, okay, I want to send data to, I don't know, 123.64.7.2.01 is not how you would write that. And I just know that this is B and I just send data to B. Because that's how it works. You have to memorize the addresses. But the thing is, humans are bad at memorizing numbers. So what if there's like, instead, we'd rather memorize words? And this is what domain names come in. For instance, we have www.google.com. Like, you're not going to remember what the IP address of Google is. There may even be several because they're pretty sure they have more than one server. But it's easy to remember www.google.com. And it's harder to make a mistake if you're like copying that from somewhere.
I'd agree. Yeah. That's much more memorable.
So it's much memorable. So we just know this. We know B. Let's say B is Google. So knowing the domain name, how do we get B's IP?
That's when the DNS comes into play because that's like a big cache.
That's what DNS is for. DNS stands for. What does it stand for?
Dynamic network stack.
Not exactly. It stands for Domain Name System.
Ah. King Pun says domain name server. Zaria says domain name service.
Service system. Yeah, I'm pretty sure. I'm not actually sure what the S stands for this time. Yes, it does stand for system. I was right. But yeah, you could do a domain name server, or typically abbreviated as NS for name server, is basically a giant database of records. And what are these records? Well, there's different types of DNS records, really. The simplest type is the so-called A record for address, and this maps a domain name to an IPv4 address. So if you, for instance, buy or rent a domain, and you have a VPS or some other server, then your VPS has an IP address, and you want to, um, for instance, run a web server on that IP on that physical server, and you want that to serve a web page to your domain. What you can do is your provider typically has a way for you to register an A record for your domain name to your IPv4, and you just have to enter your IP address, and then everyone who asks then can ask the name server, okay, who is this domain name, and they'll get routed to your IPv4. That's only one type of record, though there's other types too. For instance, you have a quadruple A record that's for the same thing, but for IPv6, because an IPv6 address is 4 times as big as an IPv4 address. And then there's some other records. There's the opposite, which is a pointer record, and that maps an IPv4. I believe it's IPv4. I'm not sure if it's any IP or just IPv4 to a domain name. If you want to do the opposite, if you want to ask, okay, who has this address? Because that's also something you might want to know. Who is this? So that's the domain name system. And DNS works. Okay, how do we actually send a DNS request, or how do we do that?
Through an Ethernet frame.
Well, that's if you have a name server in the local network, sure. But typically they're not.
So you need to, oh man. So you need to know the IP of the DNS server.
That's correct. That's one thing. You need to know. That's one thing. The IP and Excalibur is lagging a bit because the canvas is so big. That's why my handwriting is deteriorating. It's not just because of me. The IP of the name server, and those are typically hard-coded, and those are very easy to remember. Popular ones include 8.8.8.8. I believe that's Google's. And there's 1.1.1.1, that's Cloudflare. And these are some of the so-called root name servers, because you can have different name servers that delegate to other name servers and so on. At the very top of the hierarchy are these root name servers. So that's one thing. We need to know their IPs, but how do we actually send data to them? We can't just throw it in an Ethernet frame. We need a bit more than that. What protocol should we use for this?
I don't actually know. Because it's not going to be like UDP, right?
Why not?
I guess I figured that's too high level and there'd be a chicken and egg scenario, but that's probably, UDP is probably simple enough.
Well, UDP we only need in order to be able to send IP packets, we only need the IP address, and we know that.
Yes.
And UDP is just the source port and destination port. I don't actually know what the port for DNS is right now, but there is a well-defined port for that. So our choice is between, it has to be a transport layer protocol, so our choice is between TCP and UDP. What makes more sense for a DNS query? TCP or UDP?
UDP.
Why?
Because TCP implies a two-way connection that like you need to send and receive from both sides. And I don't think that's the complexity that we're at right now, because all we need to do is send a small message, right? A string, basically, and then get back the IP address.
Yeah, well, that's partially right, but you could express it a bit more clearly. It's incorrect that you do need to receive data because you need to get the response back. So you need to send in both directions. But it's true that TCP, for just sending and receiving a single packet, TCP is has way too much of an overhead, because you need to connection establishment and tear down and everything. And DNS queries are very common. Like, you need to do a lot of these at a time. And if you do that over TCP, that's a lot of just unnecessary overhead. So yes, we're going to use UDP for this, and that's what we typically use. We use UDP because that's all we need in this case. And if a DNS query just gets dropped, if the server doesn't respond, then we just send it again. Like, we just try again. In this case, it's fine. It's easy to deal with packet loss here than to try and do a connection establishment, especially since DNS packets are rather small too. So it's easier to resend it than to try and be reliable about it.
That makes a lot more sense too, because it's like, it's not imperative of the order that you get these in. It's not imperative that like, if you make a request, you absolutely have to get one back, otherwise things are going to go wrong.
Yeah, it's not that important. You can just try again.
Yes.
So this is typically how we get someone's IP address. So there's one more thing we need to discuss. It's also another thing we've glossed over.
Okay.
MAC addresses are hard-coded, right?
Yes.
What about IP addresses? How does A, for instance, even get an IP address?
It's allocated one by the ISP, right? Sort of.
Well, yes, sure, your entire network has a public IP that is allocated by the ISP. Sure, but internally on the local network, how does it get an IP? Because
Ah.
that's not has nothing to do with the ISP.
Mr. Mugume says maybe they just say that's mine now. They just say, I'm this.
Sure, that sounds very stupid, but that's one way. Yes, that's one way of doing it.
Sounds logical, doesn't it?
I believe. Yeah, that's go. Oh yeah, that's the acronym. It's I forgot what the acronym was. It's called. It's called this, which stands for Automatic Private IP Addressing.
Apipa.
Yeah,
Isidiush says router. The router assigns a private IP to every device on the network. Oh?
I believe there's different names. This thing is also for this. There's different names for this. I think this is what Windows calls it. Then there's automatic IP, auto. There's like 10 different names for this thing, and it's all the same thing. It's what auto IP is called, or what were the different names? Let me look this up quickly. There's so many names for this always. Hold on. Okay, hold on. What's the thing? Hold on, hold on.
SLRX says I always get 127,001.
Yeah, we'll talk about that in a second. Okay, hold on. What was it again? Where was that? I'm trying to find this thing, but I'm can't seem to be able to. Anyway, there are different names for this, but that is essentially one way of doing it. You send out an ARP request asking, basically, does anyone have this address? And if no, then we use it. Otherwise, try again with a new one. So that's one way of doing it. That's not really the best way of doing it, simply because it's liable to things like race conditions, and it's also kind of janky if you think about it. Like, it doesn't sound like it's going to go too well if hosts just go around selecting their own IP addresses. So another way of doing it is just actually the network administrator hard codes the IP address. That's one way of doing it for small networks. That works just fine. You can just hard code the address.
King Bun says 192.168.69.420.
Yeah. But there's also a more modern way of doing that. I believe someone mentioned that in chat earlier, I think.
Oh.
There's a protocol for this. Oh, do you know of any
DHCP. I remember now.
DHCP? What does that stand for?
I don't know, but I'm going to go ahead and guess. I like the word dynamic, so we're going to go with dynamic.
Mhm.
What is H? Dynamic Host Control Protocol.
Close. Dynamic Host Configuration Protocol.
Ooh. His use says domain host control port. Zarya says dynamic host configuration protocol. Ooh, he knew. King Bun says, yeah, that was darn close. I gave it
That
a
was
guess.
pretty close. I'll give you that. That was pretty close.
Thank you.
So, yeah. And the way this works, basically, there's there are standardized messages for that. And what protocol are we probably going to use for this?
UDP.
UDP. Again, UDP. And the way it basically works like this is that the host, there's a DHCP server or several DHCP servers, and the host just sends a packet asking, okay, what servers are there? What's that packet going to look like? Well, it's gonna go over UDP, so it's gonna have port. Oh, sorry, actually, it's the other way around. So it's gonna have a source and some sort of source port and a destination port. Those are well defined. I don't know what they are though right now. Um, what do we fill in for the IP addresses? Seeing as one, oh, actually, what do we fill in for the IP addresses? Any ideas? Because we
So
sort of need to.
we're asking for IP addresses.
Mhm. But we are sending an IP packet, and that needs IP addresses.
So is there a special IP for the DHCP? Is it like hard coded like DNS?
No,
Okay,
there can also be multiple DHCP servers offering DHCP at the same time.
that sucks. Okay. Okay. So if it's not like DNS and it's not just a hard coded address, Mr. Mugume says 69696969. That's
Not
gotta
exactly.
be it. So do we just
So,
put zeros and hope everything goes well?
well, yeah, for the source, and actually this is drawn incorrectly because this would be the UDP. Can I like move stuff here? Oh, I can.
Yes.
Hold on. I'm going to grab this and move it a bit down because we need to wrap this. So this is the UDP packet. We need to fill in something in IP, and this is an exception because normally you're supposed to put your own IP in here, but you don't know that. So for the source IP, we put in all zeros. That's true. We don't know who we are just yet, so we just fill in zeros, and you actually just write 10, but still. And what do we fill in for the destination IP? Where do we send this to?
Is it like broadcast? FFFFFFFF?
It is a broadcast. In this case, you'd write 255, 255, 255, 255. That's
Hey!
the IP broadcast address.
I'm going to shout
So
out.
send this, and then DHCP servers are going to receive this and then going to answer with a DHCP. So this is what's the other called? What's this called again? I think this is called DHCP discovery. A discover message. This is a DHCP offer. And then the host can pick one and says, okay, I want this one, and it sends a DHCP request. At this point, it knows the destination IP, and I believe I'm not sure. Does it either it fills in zeros again or it uses the IP it's been assigned? I'm not sure what it fills in at this step. I'd have to check. But
I
anyway,
see.
once it gets back, because this can fail, but it gets back a DHCP. I think it's I don't know what it's called officially. I'd have to check. What is it called again? Because these have official names, these messages, but these are like minor protocol details that aren't that important to the understanding of how the thing works. Yeah, it's called the DHCP ACK. So, and for request, let me check. Yeah, for the request, you still fill in zeros because you don't actually own that IP address yet.
I see.
And once you get the ACK, then you know this is your IP. And what you can actually also do is in between here, if there are any race conditions, you can send out an ARP request and check, does anyone else actually have this address already? Just to be sure. And this is how hosts can or assign themselves or can get assigned IP addresses. And the thing is, this is an automatic procedure, dynamic host configuration protocol. This both means that the IPs are not hard coded and that it just works on its own. You just set this up, and if you connect something to the network, it will just get an IP. So this is how
That's how IPs are resolved or gotten.
that's how we get IPs, and DNS is how we resolve domains to IPs. And now we pretty much know more or less everything, at least from a high level, what there is to know about how networking works in general. So now you know how for instance, a web request works. You write a HTTP request. You then determine the IP of the web server using its domain name via DNS. Of course, before that, if you get assigned an IP address via DHCP or some other protocol, you then construct an IP packet. You fill in the destination IP, which you just got from the from DNS. You then put that entire thing. The port, by the way, for TCP or UDP, for the TCP port is well defined, so you just fill in 80 for HTTP or 443 for HTTPS, or also some other port if you want to send it to a specific port, because you can do that if you put a colon after the domain name in the URL in the browser, it will send it to a specific port. And then you grab the IP packet, you put that inside an Ethernet packet. And what do we fill in for the MAC address? Well, if the destination IP is on the local network, which we can check by looking at the network prefix and comparing those. And if they're the same, we get the destination IP via ARP and send it on the local network. If it's not on the local network, we just send it to the router. If we don't know what a router is, we send it to the default gateway, which is our network prefix with .1 at the end. And the router takes care of everything else. And for receiving a packet, it works just the same way, but in reverse. Except that, well, the destination, the receiver will already know where to send it to, because we are sending along our IP address and our MAC address, which will be relevant if we're on the same network. And that's how you make a web request.
That's amazing. I feel like I should clap. That was like the end of an amazing TED Talk. And that's how you make a web request.
Pretty much. So now you can implement a web server in LensorOS. Let's go. Shouldn't be hard, should it?
Easy. Easy. King Bun says, yeah, I'm crying right now. Don't even know way. Molly the Man says, hello. Is it use a standing ovation? Everybody's
Are there
standing
any
and clapping.
questions about anything here, really?
There haven't been, but if anybody has them, feel free to pop them in the chat before we move on. King Bun says, can you sign my left pinky? Not the kind of question we're thinking about, but sure. Just send it to us in the mail, and we'll send it right back.
Via HTTP, please.
Send your finger via HTTP so I can sign it. Oh, that's so good. I want to shout out Nomadic for Life, Sam AHT, Samet Ilek, and Pony Lover for the follows during today's stream. I appreciate it so much.
I just want to also mention that there are a few things we haven't gone into, like the internal workings of TCP. We've pretty much discussed most of what there is to know about the network layer. I mean, there's ICMP, which is also a protocol. What's that? The Internet Control Message Protocol or something like that. I'm not actually sure what ICMP stands for, honestly. I mean, there's so many abbreviations in networking, it's horrible.
There really are.
Control Message Protocol, yeah, I was right. So that's basically also is sent. I'm pretty sure it's sent over IP. Actually, it's not, but not UDP, just IP, and it's basically used to send control messages back. So if a packet gets lost along the way because it's an IP packet has a hop count, meaning it can only be forwarded so many times until the network decides, okay, this thing isn't going to arrive, and just drops it to make sure packets don't get stuck forever. And if that happens, the router that drops it sends back an ICMP message telling the sender that, hey, that thing got dropped. And also a common there are several ICMP messages. One of them is the so-called ICMP echo request and the ICMP echo reply, and that's what is also commonly known as a ping. So if you ping something, one way to do that is via ICMP. That doesn't mean it's always done over ICMP, simply because, for instance, on Linux, to send ICMP messages, you need to open a raw socket, which you can only do as root. So if you want to, for instance, ping someone as, well, not root, that's typically done by sending a UDP packet, I believe. But ICAP is the traditional ping, if you will.
Interesting. So,
But also because of that, a lot of networks also block ICMP sometimes to prevent spam and so on.
interesting. So, you can't
Yeah.
ping unless it's like some very specific permissions because it's a specific protocol.
Yeah, because ICMP is generally the kernel only exposes TCP and UDP. You don't really get anything below that unless you open a raw socket, which you can only do as root. So yeah, on Linux you can't send ICMP messages just out of nowhere unless you're root. So that's why we typically use, or if you could use ping on Linux, I'm pretty sure you use UDP instead because you can just send UDP packets instead.
Interesting. That makes sense. So it kind of it's just so interesting to me that like what seems like the simplest thing to do on a network, which is like ping, it's actually like really complex and requires root permissions and but it makes sense if you break down why
Yeah,
through this
also
whole step.
ICMP as a protocol, it's called the Internet Control Message Protocol. It's for control messages to say, okay, network unreachable or something got lost or whatever. It's not really meant to send ICMP messages that much as a host. You just mostly receive them. It's
Interesting.
mostly routers that send them, I believe, I'm pretty sure. So there's just no need for the kernel to expose that simply in the same way that it doesn't expose like IP. And also because as a security measure, because on Linux there's this thing called IP tables, which is basically how the firewall you can configure. Okay, certain addresses are allowed. Yeah, you're allowed to receive UDP over this port from any address, but you want to drop any TCP traffic that comes in from any of these addresses and so on. You can configure that as
So
in various different ways. But the thing is that raw sockets just bypass that. If you open a raw
ah
socket on layer 2, you can just receive and send anything. Which is why, for instance, they bypass firewalls, which is why, for instance, if malware gets to run as a root, they can just open a raw socket and then no matter how your IP tables are configured, the packets still get through. They can still send and receive and do stuff.
so when you're saying firewall, that's kind of like an allow list or deny list of IPs.
Yeah, pretty much. IPs and ports and protocols typically.
So it's a deny list specifically.
It's sort of both. You could set it to, um, I don't know the syntax off the top of my head, but you can like add a record by saying, okay, we allow from whatever this address. I'm not sure this is the exact syntax. I'd have to check. I haven't done this in a while. For UDP
Ah,
on like port 42, or like we allow from zero, typically 0000 is used for any address on, for instance, if you're a web server, you're going to allow TCP incoming on port 80 or whatever. And then if you then there's two rules at the end. Typically, there's basically something along the lines of drop anything else. I'm not sure you spell this again. I haven't done any IP table setup in a while, but you can either do drop anything else or allow everything. That's like the final rule at the end. So you can have both an allow or deny list.
that's very cool. So it's kind of just limiting certain IPs to certain protocols to certain ports within those protocols.
Yes. I can also say, for instance, you can disallow ICMP echo requests here.
Ah, okay.
For instance, you can decide not to reply to them.
Is it usually says so like just a list, not an
Hmm.
allow list or deny list. It's just a list.
It's just a list, yeah.
All of this to just say ping google.com. Exactly.
Yeah, ping.google.com is fairly complicated. So if I look at my IP, yeah, there's an input, a forward, and an output chain by default. Input and out. Input is for incoming stuff. Output is for outgoing stuff. So I can also control who gets to send to where. So if you're writing, and it's a common thing, be careful when you configure IP tables. If you set the default policy to drop, make sure you allow SSH access. Otherwise, you won't be able to get into your server anymore. If you
Oh
just say,
God.
okay, block all TCP traffic, while and then suddenly your SSH connection becomes unresponsive. Yeah, well, sucks for you.
King Bun says this sounds like something from experience.
Yes, it does. Happened to me once. Luckily, the thing about IP tables is that they're transient, meaning if you reboot, they're gone.
Very nice.
There are packages you can install that kind of you can save the IP tables to a file and then they reload them when the program starts. So you can just set a systemd service, I suppose, or a cron tab or whatever. And but luckily I hadn't set that up yet, so I could just reboot the server remotely and
Nice.
SSH back to it. But yeah, be careful when you set that up. Because you have to make sure to both allow incoming SSH traffic and allow outgoing SSH traffic. That's the hard one. That's the one you can tend to forget about. You tend to forget about not both, but just either one or the other. But you have to
Right.
allow both, otherwise, yeah, it's not gonna work too well.
Uh, Zarias asks, did we talk about CDN?
Oh, that's not really
It's another layer.
well, a
It's kind of just an
CDN isn't really it. It's kind of something on top of all of this. It's like really, I'd classify it as an application layer, really. I mean, it's difficult because a CDN is a CDN is a content delivery network, which typically works via proxies or reverse proxies. And a proxy server is basically, or a reverse proxy is a server that takes an incoming request and forwards it to a set of other servers. That's a way of like load balancing so that not you don't have one server for everything. You can distribute the load, or you can dynamically choose to if you're like loading or getting video data from somewhere, you can say, okay, I want some of the frames from here, I want more data from here, so that you don't hit the same server with everything. That's a CDN basically.
so like
That
if you had a file foo.txt
yeah.
and you're requesting it from a CDN, it might give you the first half from this one server, but then a big request came in on that server halfway through, so now it switches to another one that has less traffic.
If it's a particularly large file,
A
perhaps, or
huge,
maybe
yeah.
you'll get one file from this with the next file from the other, and so on. And often you'll get several, or the front end or the client might even get a list of several servers, and then it will pick out between one of them or just cycle through them or whatever. This is really something that's it doesn't really it is networking in a way, but it doesn't really have anything to do with like the essentials of networking that we just discussed here.
We'll never
It really
implement this
like
in code.
high level concept. Come
Yes.
again?
We'll never implement this in code.
No, we don't won't need a CDN for anything.
The LensorOS CDN.
Yeah.
Well, I have a question. Is it
Hmm.
bad to like send an Ethernet frame that doesn't make any sense?
I
What
mean,
if you just send garbage over the Ethernet?
you can do that. No one's like they're just gonna, yeah, that's garbage. I'm not gonna look at this. This is what they're gonna do.
So they're
Like you
just
can
going
do
to
that.
ignore it.
Yeah.
Okay,
Unless
so
you
it's
happen to
not going to
have a
like,
frame that just happens to be a valid something.
right.
Then they're gonna react to it somehow.
So what if one is just slightly wrong? Like let's say you send an ARP, but the checksum and the Ethernet frame isn't good.
Checksum is wrong, it gets rejected. That's what the checksum
Rejected
is for.
where? Does it
Whoever
make it
receives
out of
it
the
will, depends what checksum is wrong. If the Ethernet checksum is wrong, I'm pretty sure that the link layer that receives it will just discard it because they'll check the
Yes.
checksum and see, okay, this because if the checksum is wrong, that means that indicates that there was an error in transmission, that the packet is faulty somehow, and they're not going to accept the faulty packet. They're just going to discard it. Whether the checksum calculation is wrong or the data got corrupted, and that's where the checksum is no longer accurate, that it doesn't know that, so it just discards it.
That makes sense. That
That's
makes
still
sense.
true for any checksums on any layer. Like if you have UDP packet with an invalid checksum, it also just gets dropped. Or an IP packet with an invalid checksum.
That makes sense. King Bun says Lenser Package Manager CDN. And then garbage is sent over Ethernet frames all the time. Check my last stream. Oh, that's so good. Even my packets are ignored. I gotta add Bible Thump to the plugin for Emacs.
Mm-hmm.
Get that binding of Isaac going. So I've been hard at work here in the background.
Mm-hmm.
I think I've actually done it. I think I've initialized transmission. So we basically allocate our ring buffer and then set all these hardware registers based on some stuff from the manual. And then we enable transmission control, pad short packets. So it'll make short packets longer automatically. And then the collision threshold and collision distance, I just did the defaults. I don't know what these mean.
Okay, so this is like very low level stuff.
Yes.
So basically, I'm not really sure how exactly in the Ethernet standard that's defined, but basically, there's things about the way you send data on like a link is, and this is like, we didn't discuss this, but this is technically still part of the link layer. This is like part of the aforementioned medium access control sublayer. Is on the if we look over here real quick, if you have an Ethernet packet, and draw it real quick.
Yes.
If you have an Ethernet frame, sorry, this is an Ethernet frame, then how does the physical layer know where a frame starts and ends? Because sure, it has a size in it somewhere, but at least I think it has a size. I'm not sure even if the header has a size, but that's kind of a bit annoying because the physical layer deals with individual bits. So yeah, they're not going to do it this way. So what you do instead is you have a start of frame delimiter and an end of frame delimiter. And I'm not sure where it is. It's either before that or after that conceptually. And if you have another packet, so we can actually draw it this way. So we have this packet with the start of frame and end of frame delimiter. And this entire thing is sometimes called an Ethernet packet instead of a frame. So this is the Ethernet packet. And between these packets on the physical layer, this is the interpacket gap here.
So
What default values for these are, I'm not sure if that's how well defined that is in the standard, but this is what that means basically.
I see. So a frame, we know where the start of it is.
That's this yeah.
Because this delimiter, start frame delimiter, tells us where the frame starts.
So you actually, do you really have to encode that? Does the NIC not do that for you?
Yeah, I don't think so.
Really?
So the SFD is a 1 byte value that marks the end of the preamble, which is the first field of an Ethernet packet and indicates the beginning of the frame.
Yeah, that's on the physical layer. That's an Ethernet frame on the physical layer. Like typically the actual Ethernet frame proper is just the head, if you scroll up a bit, because that's the packet on the physical layer. This is the actual, now this is, if you see layer 2 Ethernet frame, that's the actual Ethernet frame, starting with the destination MAC and ending with the frame check sequence.
So what you're saying is that we actually just need a layer 2 Ethernet frame.
I hope we only need the layer 2 frame.
Okay, so that means I can simplify this a little bit.
I'd really hope we only need the layer 2 frame, honestly.
We don't need
I mean,
these.
it depends on the NIC. We might have to throw the interpacket gap and like everything before and after it, but that would be on the physical layer, so I'd be honestly a bit surprised if we had to do that as well. But
In which
that depends.
case,
You'd have to check what the NIC says. I'm not sure here what exactly we need to do. But on the link layer, that you can see that's just the actual frame is just starting with the MAC, ending with the frame check sequence, which is the CSC32C, I believe. Yeah.
okay. So Where are we at? So Ethernet frame footer, this is technically just a U32 now.
And since we're talking about protocol type, I haven't addressed it since we're talking about the Ethernet headers already. The protocol type is determines what protocol is inside the packet. So that can be like ARP or IP.
I see.
IPv4 in this case, yeah. Apparently, these are all well defined somewhere, I think, also by the IANA.
Yes, this is all defined by the IANA as far as I know. I was reading from Wikipedia, which talks about the same thing. IEE 802, all this stuff. But yeah, so this ARP, this is the data that we're going to send.
The entire packet, actually, yes.
So this is like the data that we're going to send in between the header and footer of the Ethernet frame.
Yeah, that's the data that goes, that's the frame data, yes.
Okay, so this ARP, exactly like you're talking about, we have a sender and a receiver, or a target, right?
Yeah, those are the MAC addresses.
Yes.
And the IPs, like the 6 bytes are the MAC addresses. The hardware address is link layer / Ethernet address, and protocol address is IP address.
Yes, because it could be any protocol, but we're requesting the internet protocol address.
I don't think it's ever anything other than IP. It's just called protocol address. I don't think ARP is ever anything other than IPv4, because IPv6 doesn't use ARP. It uses what's neighbor discovery protocol, NDP is what it uses, which is ICMPv6 basically.
I see.
It doesn't use ARP, so I'm pretty sure it's always IPv4.
Yes, and then we do some basic configuration just based on what these actually say.
Sure.
Like for IPv4, this is OXO 800.
Ethernet. That's if you. I'm not terribly familiar with Wi-Fi networks, but I'm pretty sure you might have to put something else in there if you're dealing with a wireless network. But I'm not that familiar with wireless networks, so
I'm not worried about that right now. So the ether type for blah. So basically, what we're saying is that the ether type in the Ethernet frame header will be ARP. However, the ether type within the actual ARP is going to be IPv4.
Yeah, because ether type in the Ethernet packet determines what's inside the packet, whereas ARP data, the Ethernet, quote unquote, the hardware type tells it what the type of the link is. So yeah, in this case, Ethernet.
Okay.
It feels a bit redundant. That's true. I'm not actually sure why we have this hardware type in particular. But the thing is also with some of these is that there are simply redundant fields in there sometimes because these protocols are old and they thought, yeah, well, we're gonna need to have we're gonna have different protocols eventually, right? Yeah, well, no.
So do we now need to put the ARP in an IP packet,
No,
header?
just in actually,
because we need to actually specify addresses.
I'm pretty sure. Okay, I haven't done ARP in a while, but I'm pretty sure you won't put that in an IP packet. It just goes in the Ethernet packet, right?
Well, in that case, what address are we resolving?
Well, what address do you want to resolve?
Let's say like localhost.
Well, the localhost is a bit special.
Okay, or like the router, the address of the router.
What's the IP of the router?
It's going to be 192.168.1721 or something.
Could be, depending on what your local network is.
So
it doesn't right now. You don't need to send a valid ARP request. You can just put some random garbage in there and ask, "Does anyone have this address?"
I just don't. So where are we actually specifying which address we're resolving? Because I don't see it in here.
So an ARP packet has what it has. An important thing is that you shouldn't confuse the MAC address in the Ethernet header from the MAC addresses in the ARP packet. Those are different. The Ethernet header. So what do we put in the Ethernet header for destination source?
Well, for source, it's going to be us, our MAC address. For destination, it's going to be, oh man.
Who do we actually want to send this to? This is whom this actually gets sent to.
It's a broadcast packet because it has to go to everybody, right?
Yes, so we put what in there?
OXFFFFFF.
Yeah. Like ones, just ones.
Yes. So,
So what do we
okay.
put in the R packet? We have a sender hardware and protocol
Oh,
and
and then
target
this is
hardware.
just our IP and our MAC address.
And what do we put for the target?
I'm assuming it's ignored, so zeros.
Careful. How do we know what IP we want to resolve?
So we have to put the IP here.
Exactly. Target protocol address, that's the IP we want to
Uh,
resolve. Target hardware address, we don't know that yet, so we set it to all zeros.
I'm starting to
That's
get
the big
this
one to
now.
figure out. Mm-hmm.
So this is the IP that we want to resolve,
Mm-hmm.
and we send that to everybody, and someone hopefully responds with another ARP packet or ARP anything, and it will have reply set as operation, and then the sender hardware address and protocol address will be the IP and MAC address of whoever had that IP.
Mm-hmm.
And we can ensure that what we get back, the sender protocol address, matched the target protocol address we asked for.
Pretty much, yeah.
Beautiful. King Bun says,
What I'm actually going to do is I'm going to take a screenshot of an app request, edit out the MAC addresses, and then I'm going to send you a screenshot so you can see what it looks like, maybe.
beautiful. Yes, that will help a lot. So assuming we have an ARP ether type in the header, we now, okay, we also have to set MAC source. Okay. So we have the source MAC address set now. The dest is going to be broadcast. Okay, so we have 6, basically all ones. We have the source address, we have the ether type. That's the Ethernet header completely done.
That's good.
Pog. Okay, so now for the ARP, Ethernet hardware type is 1. The protocol type shares the namespace with ether type, and it's IPv4, which is OXO800. According to Wikipedia. I don't know that, but that's what it says right here.
Correct. I don't know them off the top of my head either. No one does, I think.
The length of the hardware address that we're supplying within the ARP sender, right, is 6. Because it's a MAC. So basically, we're in the ARP, the source, the sender hardware address is the 6-byte MAC address.
Yes, that's the MAC address.
So that means that the hardware length, right? Is that where we're at? Hardware length is going to be 6.
Should be, yes.
Because of Ethernet. Yes. Okay. And then IPv4 address is 4 bytes or 4 octets. So the protocol type and length match up, as well as the hardware type and length. And then the request operation is 1, because a reply is 2. So if there was some address, if someone was trying to get our address and we realized, oh, we received an ARP, it has our address, we need to respond, then we would set this to 2 and specify the sender hardware address in the same way, right?
The operation is sent to reply or response, whatever it's called, and we do the other way. Yeah, we fill in everything but the other way around. Yeah, we fill in the sender hardware and protocol is our hardware and protocol, and the receiver or target, in this case it's called hardware and protocol. We know that because that's the source of what sent the packet to us.
That makes a lot of sense. So with our ARP set up, do we have to specify our own IP and our own MAC address? Or is that just like extra? Do you only ever need one of these?
No, you typically specify all of them. You specify everything you know.
Okay. So how would we figure out our own IP?
See, that's the thing, the HCP. Or if
That's
we don't
right.
know
That's right.
the HCP, we need to kind of make one up, I suppose.
Okay. Well, we've done it. So now, target protocol address. What's an IP I can make up? I guess it can be any IP. It just has to be the fact that.
Ideally on the same network as you are on.
Right. So how do I know that?
You could look at your local IP.
Yes. Let me try and do
On
that
Windows,
without.
I think it's like in CMD IP config A or something.
Let me try and not dox myself here. Yep, that would be it. And then I know which one I'm on. So it says the IPv4 address, and then the subnet mask. So I can use the subnet mask to get the
The
network
network
IP, right?
prefix. And then you just grab the network prefix and make up any IP
Here's the
that
thing.
starts with the network
If
prefix.
people know the network prefix, is that a problem?
No, it's local. It starts with probably like 192 or something.
It does. So
192.168, right?
what can't I tell people at this point? Is it the
If your
last
address,
number?
no, it doesn't matter if they know that your local IP is 192.168, whatever it is. Local IP doesn't matter because, okay, we haven't talked about this. That's called NAT, Network Address Translation. And basically, what happens is, yeah, the router has both, and it provides the local network with so-called local IP addresses. Those are only valid on the local network. Your public IP is a different one, and the reason why this happens is because your router has one IP. You get that one from your ISP. That one is the one that you don't want people to know. That's your public IP. But you somehow want to be able to like do something similar to ports, or you want to multiplex requests to several hosts inside the local network, but outwards you only have one IP address. So what do? Well, the router actually does some trickery with ports to map this one external IP address to all the internal local IPs, which means those local IPs are only valid within your network. And the thing is, my local IP, for instance, is also 192.168.1. In this case 207.
Okay.
So that doesn't mean I'm on the same network as you. In fact, as a matter of fact, there are three groups of addresses. The first one is 192.168/16, then 10/8. So 10 and everything after that. And the third one is like 172.1 something dot 24 or whatever.
Oh, yeah, I also
No,
have that
not
one.
24. It's like times, it's I think 12, not even. It's some random thing. I don't know what it was. But anyway, and these three ranges of addresses are classified as private addresses, which means that public routers don't forward them, which means it is impossible for this is always a private IP. If it starts with 192.168,
So
it's
you can,
always a private IP.
this is
So this
local
can only
network
ever be
only.
a local address. Yeah, this can only ever be a local address.
Beautiful. Well, I believe we're at that time then to try and compile it. That's probably step one. I can close this. I can do, where am I going? Here. Okay, let's see what happens. Oh, dear Lord. Okay. Cannot convert ARP data to const void pointer.
All right,
Yes.
so what I'm gonna do is I have a screenshot of an app request here with my MAC address edited out. I'm gonna post that on the Discord.
Beautiful.
Make sure that everything is right.
Are you okay with showing this on stream, or do you want just me to see this?
No, it's I've edited out my MAC address. There's nothing interesting on here.
Okay. I just want to make sure.
Yeah, one sec. I just gotta check. I've really edited everything out, and I believe I have. So yeah, that's it. So in this case, you can actually take a look at this. If we take a look at this, everyone where it says
Ah.
host MAC, that's where my MAC address was. I've edited it out. And you can see this is a screenshot from Wireshark. So on top you have the Ethernet header, which has the destination, which is in this case a broadcast. And the
Right.
source is my source address. And the type you can see is an up is up. So
0806.
0806. And then below that you have the packet data, which is in this case hardware type is Ethernet, protocol type IPv4, hardware size, protocol size, it's a request.
POG.
There's my source MAC address again. Then the sender IP, this is my local IP from my PC, and the target MAC address, we don't know that. And then the target IP in this case is 192.168.1.117. I was doing an ARP scan earlier, which means I just go through all addresses and ask them, what's your MAC address? This one didn't
Nice.
respond, obviously, because I don't have anything on my network with this address, but that's an example of an ARP request.
This is beautiful. This looks exactly like what we've done. What are you mad about now? Okay, I forgot a bunch of address ofs. Slightly important when you're doing mem copies, it turns out. To get pointers to things. Assigning to an array from an initializer list. That's not allowed? C++,
Oh
why?
wait, what are you doing? Okay, is it a C array? You can just make, do we have standard array?
No.
We can implement standard array and we use that instead.
Let's do that right quick.
Sure. Yeah, this is very easy to implement actually standard array. It's trivial. Let me quickly check if you can really make a standard array and assign to that. I'm pretty sure you can. So if we have a standard array of int for ints, call it A, then we can assign 1, 2, 3, 4. I think we can do that. We can. So we can just add standard array real quick if you'd like. I'm not kidding, by the way. It's really easy.
We can. That's a good idea. We will do that, but I do think I fixed it. How do we fix standard array?
I'll be right back, okay?
Okay. We'll see how it goes. We're on our own, folks. What did I forget now? So, did I forget? Everything looks fine here. What do we got? We have an error. Missing initializer for member MAC source. So it's saying the missing initializer for member. Okay, don't initialize it then. Oh, there's also no semicolon there. That might hurt things. Ozirix says you can ask for a static one with DHCP, I think. Probably talking about IPs. Ozirix says, hi. What's up, Ozirix? Is it used? Yeah, the generally used when you want a static IP. Ozirix standard array supports initializer lists. Kingbone says, and the stream's on fire. Is it really? I've turned off my viewer counts and everything, so I don't see that stuff anymore. Is it used? Says, as far as I know, and also hi Ozirix. Well, hey. Okay. Frame check sequence. Inline specifier invalid for variable buffer size declared at block scope. Okay. Well, I'm getting there. Don't worry, folks. Missing initializer for member blah. ARP data, ARP0. Didn't I get rid of that? Am I crazy? Okay, I got rid of the first two. The first one, not the last two. King Bun says no, just joking that Sir Aid left. Ah, I see. Yeah, it's definitely going downhill from here. Oh, LensorOS is starting. Pog. It compiled. What's going to happen, folks? What is going to happen? Triple fault? Well, we didn't get a triple fault, so there's that. What do you know? Well, it works. It seems to have worked. Although I don't see... okay. So, I don't think necessarily anything happened. Let me try again. Novag, I don't know how to say your name. Novag says, wait, what? You definitely can do C arrays with initializer lists, no? What C++ are you using? C++ 23 or something? 20? Okay. Well, nothing happened, so nothing blew up, I guess is a good step one, right? Everything's fine. We seem to still be getting our MAC address, right? So we still are getting our MAC address. Are we getting any interrupts? Oh, I wonder if interrupts are disabled and it's causing us to miss it. Well, the one way to do that would be to wait until after interrupts are enabled to actually do the thing. This is such a mess. Is it huge? Says, oh, Lens, it's the calm before the storm. I have to go soon, so yeah, pretty much. If you haven't already, be sure to check out the Discord like Zarias did today. Shoutouts to thems. And yeah, we got you get announcements every time I go live. We got memes. We got fun times. You can influence what happens on stream. I asked, what should I do today? So yeah, I recommend all that stuff. Well, again, it didn't blow up. Did we get an interrupt? We didn't get an E1000 interrupt. If we didn't get an E1000 interrupt, that may mean... Well, I guess if the checksum is invalid, the NIC may just refuse to send it at all, right? Novag says, I meant C-like arrays. I know he's using C++. Can I post a link? Yeah, go for it. We'll see how it goes. I'm not going to click it, but you can post it. I'll let other people click it first. Okay, well, I guess what would be ideal to do? How do we calculate the CRC32? It's going to be a mess. I don't really want to do this. Noveg says it's Compiler Explorer. Nice. Yeah, we use Godbolt a lot around here. What do you have? Char list 10 equals 1, 2, 3, 4. I mean, yeah, you'd think it would work. And it apparently works here in C++. And what standard? 2B. What about 20? Interesting. I mean, this is where we're at. We're at C++ 20. So, yeah, I don't know. I got fatal warnings that made it not work. I don't know that. I don't know. I can show you. Or it's not going to happen again, which would be sweet. But I don't think it's going to work.
All right, how's it going?
It's going good. What do we have now? Yeah. So Novag didn't believe me that this warning exists. And then he sent me a working Godbolt link to where this error doesn't occur. But it
Assigning to an array from an initializer list. What?
Yeah, it's this when I tried to do this because we don't have standard array.
Mm-hmm.
And he said that in C++ you can actually just do this and it doesn't matter. And if you click on the Godbolt link, if you want, I can send it to you or the Discord.
Is it in a declaration? Because that doesn't... Yeah. Very funny. That doesn't... Okay, put the thing on a new line and do list equals that.
Oh,
yeah.
Wow.
That's not how it works. Declarations are different. Of course you can do it in a declaration. Yeah, you can even do that in C in a declaration.
Because that's static initialization.
Yes. Well, no, it's not static initialization. That's something else, but something like that.
Yeah. It's kind of confusing.
Direct initialization is the right term. Is you can even, if you go back to the Godbolt link.
Oh, yeah. Yes.
Put that on the same line again and remove the equal sign.
And it still works. Yeah. That makes much more sense.
That's just this. It's just list initialization or brace initialization or whatever you want to call it.
Yes.
You can't assign to it because arrays are scuffed. C arrays, that is. Also, I
Very.
saw earlier in I believe we do have an array file in include. I saw one. So, do we have standard array or do we just have an empty array?
I actually don't know. I gotta go
Because I think I
look.
saw an array header in there.
Okay.
So what are you talking about? We have standard array there. It's right there.
I've never seen it used.
Well, we've not needed it so far.
That's
Fixed
fair.
size arrays, you rarely need them. But there's your standard array.
So
Not sure if that accepts an initialize list constructor though. It
yeah, I
probably
don't
has
think
one.
it does.
I'm not sure if we have implemented the initialize list constructor.
I
I'd
don't
have to
think we
check.
have. Because the
But we
same
can add it.
problem with vectors.
Oh, vectors don't have them either. Really?
Yeah.
Oh, god. Okay, I need to add that at some point.
Uh, so nothing's showing up anywhere,
Thing is, for arrays, it looks like, according
but
to CPU
nothing's
reference at
going wrong.
least, uh, constructor, destructor, as well as the assignment operator are implicitly declared, which means it should just work. You can try it out. If you do a standard array instead, maybe it just works.
So is what you're saying is I don't even know how to do a standard array.
It takes two template parameters. The first is the type, the second is the size. Yeah.
Okay. And then I
And then
just do
remove
this.
the thing at the end and just do this. And then of course, if you now need a pointer or its size, you do dot data then. Oh god, careful, not all of them. Yeah.
What
So
is
now if you want to copy to it, you actually need to do dot data to get a pointer to it though.
to copy to sender hardware address?
So you need to do, instead of that, you do dot data. Yeah. And you should just be able to assign to the target protocol address now though. Let's try that. Because if it is just aggregate initialization, it is just aggregate. Yeah, it should just work actually because it is aggregate initialization. That's true. Narrowing because I've declared. Can you delete the constructor maybe? As scuffed as that sounds, you can like comment out the constructor
In standard include?
in array. Just comment out the constructor. There you go.
This thing.
This thing. Just comment it out.
It's not working.
It's not working. Interesting. Okay, I'll have to check. I'll have to check how array works internally again. I haven't looked at this in a while.
Standard print is broken now.
Okay, then I suppose I need to check how. Okay, let me quickly see. You can put it back in the meanwhile, in the meantime, but I'll take a look at how. Just glibc. Not glibc, libs and C++ do this. I'm sure there's some weirdness going on that I'm forgetting about. Is it because it's private? Did I make it private, like a complete another buffoon? Is that it?
No.
Is it not? It is private. Good God. Okay.
What's
That
private?
probably doesn't help. So make it a struct instead. Remove the public and make it a struct instead. I think that's the problem. But may very well be the problem.
Okay. I already changed all the code.
Just make it this. Okay, we can try it later. It doesn't matter.
We will. We will.
But I think that might be it. I
Let
for
me get
some reason
that.
forgot that arrays were just aggregate initialization when I wrote this apparently because array is not supposed to have a constructor. That's right. That's arrays making array a class. Jesus Christ. Who wrote this code?
So like this should work.
Yeah.
Okay.
If you've commented out the constructor and
I have to
removed
also do
and
that.
made it a struct and removed the public.
Like this.
I mean the public doesn't do anything, it doesn't matter. But yeah, like that. Because that should just be Aggregate initialization. No. Yeah.
It seems to have worked.
So the way this works basically in C++ is with a brace initialize list like this. If you have a bunch of struct members and you pass values into the list, the struct members just get initialized top to bottom. Or for arrays, the array elements get initialized, but only if there is no constructor. If the thing has a constructor, that doesn't work. If it
Interesting.
doesn't have, it has a non-trivial constructor, but yeah.
That's always a pain point in C++ is the triviality of constructors.
And for instance, what I do in my compiler, my tree type doesn't have a constructor. So you can just declare a tree
default.
and fill in things in line.
Nice. Okay, so we fixed standard array. Cool. How do we... So nothing's happening. We're not getting an interrupt.
Mhm.
We're not getting anything, but we are not getting an error either.
Are we sending stuff?
We're trying. So we have this buffer, which has the...
delete what's the lifetime of this buffer? Can you just delete that, or do you have to wait until for confirmation or something?
That's a good point. So maybe we have to... I'm deleting it too soon. I figured that after we wrote it, it gets copied, but I can't remember.
I don't know. You have to check what the nick. I don't know how the nick works. You know the better than me.
Well, the nick uses DMA, so whatever addresses you give it are physical, and it works on them directly. But
Okay, well,
this isn't a physical address, so I believe we copy it into a physical address and then, go from there. As far as I know.
so
I think that's
are we
me.
sending stuff already, or
Yeah, we're trying, but there's nothing's happening.
have you pulled a Wireshark or something?
Yeah, nothing shows up.
Okay.
I mean, not with the MAC address.
For sure. Earlier when you were showing me this, I saw that in Wireshark, when you started, you can also select some virtual networks. Is it maybe in one of them, perhaps?
It's not, because those have to do with VMware and VirtualBox.
And that's not QEMU. That's a good point.
Yes. Which I took a look at before the stream in the adapters. And it looks like Ethernet is the only actual internet one. So I'd presume that QEMU would target that one when it's given its NIC.
I see. Thing is, interfacing with low-level networking stuff is a bit annoying because if you want to send or receive stuff from the host, you kind of have to open whatever the Windows equivalent of a raw socket is, and I'm not sure that works on Windows. It's probably the same API, but still.
Well, we're not doing anything from user space, so it's easy. We have access to everything in the kernel.
In the kernel, but if you're going to send, who are you going to send to? If you want to send to someone else, that's someone else, and you only have Ethernet. Ugh.
I mean, that's my computer right now is plugged in with Ethernet only.
I mean, you could send app requests and see if someone comes back, but if you want to send more than that, then yeah.
I don't even want to see if anyone responds back. I just want to see that our driver sent an ARP request. Even if it's malformed. That's fine. See, we write 46 bytes at blah. So we're at least getting here. So we get a descriptor, and then we get read command tail, and then descriptor plus equals tail. So this is just getting us the descriptor at the very end of the transmit buffer.
1 sec, I'll be right back.
Okie doke. txDesc tail is set to 0. So this is just going to be this. Move that closer to the actual request pages call. Okay, we do that now. So we can say, what we do is allocate
All
a
right,
physical
I'm
memory.
back now.
Cool. So this is in write raw. This is what we're calling.
Mhm.
We get our descriptor by adding tail count to the base pointer of the ring buffer. This is initialized to 0, as you can see. And after adding that, that means we'll just have this. So we get the first descriptor in the ring buffer. We allocate physical memory for the actual data, and we calculate the amount of pages, allocate that amount of pages, and then copy from the given buffer into the newly allocated physical buffer. Technically, we could just look in the page table directly and get the physical address that this maps to, but that's a little messy. As far as not every platform supports that, and relying on that means that you'll build it in a different way, if that makes sense. We check if the maximum allowed packet size happens, which it isn't. And then we just set the length of the descriptor after setting the address to however many bytes there are.
1600 bytes, that's a big packet. Does this support like
16,000.
jumbo frames or something? Yeah, 16,000 is what I meant. That's a pretty big Ethernet packet.
It's very large. I just got that from the actual manual. I don't know what that's based on. Here, transmit data
Hold on.
storage.
Line of data is another device. Well, that's a pretty big one. Okay. Jeez.
I don't think
this supports like jumbo frames or something.
Well, I don't think they're talking about frames. I think they actually mean a packet, because they say a packet consists of 2 or more descriptors.
Yeah, well, a packet is like not a lot larger than a frame. It's just like just a frame with a few extra bytes.
That's true. But yeah, so that's that number. We could probably have this be different, but that's just from the manual. And then we set the tail, the transmission tail, to 1 plus whatever it was before. There's actually a race condition here if we end up allowing interrupts while we're in here, but I don't think we will. If that makes sense. Because technically we'd have to read it twice, make sure it's the same, right? Yeah, basically we would just have to read it again, like this, to avoid a race condition. So just increment the tail. Yes. That's all we do. I think that's all there is to do. Do we actually have to set something in the descriptor that like says transmit me? Maybe command. Okay, hold on. Command. What are you? Transmit command. Pog. Okay. Oh, this is IDE VLE Dext. So I already have this here. But this is for the receive. Interesting. So I figured there was just one command, but there's actually multiple, which kind of sucks. So we're going to have to like define tx command. I mean, command IDE and VLE we can share, but Dext looks suspiciously important. Insert checksum. Ooh.
That's a good one. Yeah.
That's a very good one. So tx command, let's just start with EOP. Ooh, where did I just went I don't know what just happened. I jumped away. So end of packet is here. IFCS and insert checksum. Those are both there. Okay. Controls the insertion of the CRC field in normal Ethernet packets. It's valid only when end of packet is set. So I'm not setting end of packet. That's a huge, so it's never understanding. Okay. What else do we have? Report status. Probably don't have to set that. Report packet sent is reserved, should be programmed to 0. Extension 0. I don't know what a VLAN packet is. I'm not going to worry about it. I'm going to think about... Okay. Maybe let's just do this. The only one that's different looks to be... I'm just going to... Don't tell anybody.
VLAN is virtual network. I'm not particularly familiar with that either.
I do not blame you. This should be 1 to the left 4, shouldn't it? No, it starts at 0. 0, 1, 2, 3, 4, 5. Okay. Transmit command. TXCMD. I just try and put letters here that I'll search for when looking for this. Okay. Might also look for that. Beautiful stuff. So with this, when we write raw, the descriptor command should have command end of packet set, and it should have checksum offset start field and stuff like that is probably also important. So if we did insert checksum, it inserts a checksum at the offset indicated by the CSO field. And then the checksum calculations are performed for the entire packet, starting at the byte indicated by the CCS field. Oh, Jesus. Where are these fields? IC is ignored if CSO and CCS are out of the packet range. This occurs... Hold on. Is this a typo, or are these actually different?
What? Which one?
CCS versus CSS.
Okay, CSS. Okay, interesting. I doubt there's both. I think that might just be a typo.
Which one's correct?
Seeing as CCS is twice, it's probably that one.
I think I copied that incorrectly all the way up. Because I think when I described these, I called it... Oh, no, I didn't. I did it out. See, but this says CSS. Okay. What? I guess...
Some starts, so CSS makes sense, I suppose.
So they typoed CCS twice. Legendary. So if they're out of the packet range, it doesn't do anything. So if we screw up, it doesn't matter, is what this is saying. Very nice.
Well, we don't get the checksum, which means it's not a valid packet, so...
Which is how it is now. So if we insert a checksum, then we need to set the checksum start field and checksum offset. So what is the start field? Where to begin computing? The software must compute this. TCP. CSS providing units of bytes. So this is basically saying how many bytes into the data do we skip to begin calculating the checksum? Because we need to skip. What do we need to skip? Why is there a start field? Do you know?
I have no idea.
Okay.
I'm pretty sure the checksum is the entire packet, though. I'd have to look that up, though, in Ethernet.
So it'd be 0.
I'm not particularly familiar with the physical layer. or low-level link layer.
That's fair. And then the checksum offset just says where to write it. So this would be the length of the packet minus 4, right? Because at the end of the Ethernet frame, there's...
4 bytes.
Okay. So checksum offset is going to be equal to length minus 4. Craziness. Okay, then we can actually set insert checksum as a bit. And this should insert it if everything's valid. I don't know what FCS is, and I'm not going to even think about it.
Frame control sequence, frame check sequence, that's the same as the CSC.
So what's the difference between insert checksum and insert FCS?
Maybe IC is for TCP checksums or whatever.
So I actually need... Oh.
Because frame check sequence is the Ethernet checksum, I'm pretty sure.
So that would make sense because we don't need to specify an offset for the Ethernet one.
I was wondering why we'd have to specify an offset, seeing as it's at the very end of the thing.
So we just enable IFCS, and then I'm assuming that we just don't include the footer in the length.
Okay, that depends. You have to check the standard because sometimes you zero out the checksum and include it, and sometimes you don't. You have to check how Ethernet defines it.
Hardware only sets the data descriptors with the null to transfer no data. May be delayed. Status field.
Use the checksum. I don't think you have to specify anything. I don't think you have to add a footer, seeing as it calculates the checksum for you.
That makes sense. And it won't hurt if there's like 4 extra null bytes in the packet, right? In the ARP.
I mean, it's Zod with 0. That doesn't... Not sure that changes anything.
Okay.
Because a CSC is just a ZOR, basically.
Well, again, nothing happened. Not on Wireshark either. I guess I can restart Wireshark because it's been running a while.
You're capturing on Wireshark, right?
Yes.
Okay.
And then I'm filtering by MAC address. I didn't see any 1000 interrupt and nothing in Wireshark either. I remember there was something I was reading about in QEMU where it can dump all of its network driver, like a log that Wireshark can open.
I suppose you can. Yeah, that's the thing. Like app something is called the file format. You can search for that, I suppose.
QEMU networking. You said tap?
What? No, I don't think there's anything to do with taps. Just record networks or record traffic.
I could swear you said that the file extension is tap. Maybe I'm insane.
Oh, it's cap something, pcap and G or something.
Cap. I see, with a C.
Record network traffic. See.
Oh, Jesus.
Okay, apparently it's this.
You have it?
Where do I put this?
Discord?
Sure.
Anywhere? Mighty Baka. Welcome.
Apparently it's this. And just, yeah, it's that. That's the option. And instead of tempvm.pcap, you put whatever file name you want.
It's -net user.
It's both of these. Like,
do these interfere with -nic or are they in response?
no, -net. That's -net.
I know. I just know that dash nick is like made up of other. It's a
I
shorthand.
have no idea. It should be fine.
Okay, so
But
it's
make
net
sure
dev.
you don't have a /temp, so make sure to change the path.
Yes. I'm just gonna do. Can we do not an absolute path?
Sure, probably. We'll see.
Output dot beacon.
And you can open that in Wireshark.
If it generates it, it should. If QEMU works, I'm just expecting QEMU to be like, yeah, that doesn't work on Windows. Let's do this. Parameter type does not accept value dump.
Fascinating.
There you go. If I get rid of the nick option, does it do anything?
Apparently, like the full option is this. Hold on. Like they're doing the nick differently, apparently.
Yes, they must be. The
I
full one
send you
is
a
net nick model net dump. Interesting. Yeah, we're gonna try it. And whatever works me. I just deleted the wrong one. This is getting confusing. Little worrying. I don't set the MAC address here. So are we just going to get a random one?
guessing by the rest is probably just -net Mac.
True. And then a comma and the value.
Yeah.
Or I do it here like MAC equals. I don't know. Because up here when in nick we have model equals and MAC equals. So maybe it just goes with the model equals. Parameter type does not accept value dump. Yeah, it's not going to do that. So I can't dump to a file. Which is unfortunate.
I also love how I'm looking at Stack Overflow, and one of the answers is, since QEMU is open source, you can get the source and insert code into the network device simulation to capture and lock the data packets as they come through the device. Sure.
That's totally realistic.
I mean, yeah.
It's just
Not
completely
wrong, but it's also not right.
Well, it didn't blow up. Nothing happened, but it didn't blow up. I'm looking for an E1000 log output as a response to an interrupt, in case anyone's wondering why I keep looking here and expecting something.
I figured as much.
It looks like we got the same MAC address as before. Still, nothing's happening. So if I can't dump to a file, or maybe it's just there's a different way to do it. Include dump VM state, JIT dump. I'm just searching for the word dump. It's not in here. Okay, wonderful. Thanks, QEMU. Yeah, it's not really liking me. Can I go? Is there a QEMU internet command, like the debug command? I don't even know what I'm asking. So apparently, so there's logging we can enable apparently. So this would be something to look at. This doesn't actually have anything useful, naturally. Okay, I'm out of here. Well, What did I try that time? Oh, I'm dumb. I shouldn't have closed it. I wanted to look at the QEMU monitor and maybe poke around there. We have the QEMU E1000 code. Could look in here. I don't think that's going to help. Okay. I don't know how to get there. But there's other things. Control-Alt-1 and 2, apparently. So there's a QEMU monitor. So is there like a net? What would it be? This isn't a useful help screen. Don't know what any of this means. So system reset, system power down, SIM address, stop capture. So is there any network stuff I can get into? I would love to know. Source debug, enable, user documentation, React OS, debugging on OS. So there's nothing to debug because nothing's going buggy as far as we know. We're just not getting an interrupt. You have any ideas?
I mean, if you're not getting anything back, then chances are you're not sending it correctly for some. So.
Which is likely. How would we specify that it's sending more specifically? What are we not doing to make it not be sent?
Under something?
What was that?
Is then like a send command or anything like that?
No. The command is part of the transmit descriptor.
I see.
So this is just the part of the field of the entire descriptor. And it's the command field, which if we go and check out what it means, there's all of these, which is the interrupt delay enable, VLAN packet enable extension, report packet sent, which says when set these two specific cards, defers writing the DD bit in the status byte until the packet has been sent, or transmission results in an error. It is used in cases where the software must know that the packet has been sent and not just loaded to the transmit. So it looks like we can poll this and it will be set when it's sent, but only for these cards, which we don't have. As we are emulating the 82540 EM in QEMU. When set, the Ethernet controller needs to report status information. This may be used by a software that does in-memory checks of the transmit descriptors to determine which ones are done and packets have been buffered in the transmit FIFO. I don't know what this means. Software does it. Okay. Report status. Do we have to tell us? Do we have to tell it to tell us when it's done? I don't know. It just seems like it should trigger an interrupt when this happens. Okay, another thing, which would be embarrassing. Are we actually... Okay, we are actually enabling the GE1000 as far as I know. Because we get the MAC address and everything. So yeah. We're doing all that. That's fine. This is not formatted correctly. Oh well. We have a frame header, ARP data, the frame footer, which is just a U32. So maybe the CRC shouldn't be included, and that's screwing everything up. So you get rid of the footer and pass everything through. So we have an Ethernet header and the data, and then we're relying on IFCS to actually insert the checksum. And then we got a set but not used error. So we can just not use this. Dun dun. Why? Seriously, it's an error. There's a type def unused. This is ridiculous. That's a ridiculous warning.
Typical, that's why I disabled that warning.
Unused local type defs.
I suppose you can have maybe unused or something.
Ooh, things are very slow. That's better. Well, we didn't get an interrupt. Still no success. I've got nothing. Do you have any ideas? I have no clue. Let's just go over transmitting packets then. So for regular non-TCP segmentation packets, the protocol stack receives from an application a block of data that is to be transmitted. That's our ARP data, right? Or is that our ARP data plus Ethernet frame? Zariel says pair programming at its finest. You know what's going on? Nope. You? No. Oh well. The protocol stack calculates the number of packets required to transmit this block based on the MTU size. Cool. For each packet, headers are prepared by the stack. Cool. The stack interfaces with the software device driver and commands the driver to send the individual packet. Well, yeah, how? This driver gets the frame and interfaces with the hardware. The hardware reads the packet from the host memory. The driver returns ownership of the blah, 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 indicated by an interrupt. So we're doing everything up until here, as far as we know. But it's just not working up. Output packets are made of pointer length pairs constituting a descriptor chain. Software forms transmit packets by assembling the list of pointer length pairs, storing this information in the transmit descriptor, and then updating the on-chip transmit tail pointer to the descriptor. The transmit descriptor and buffers are stored in a host memory. Hardware typically transmits a packet only after it's completely fetched all packet data from host memory and deposited it onto the on-chip transmit FIFO. This permits TCP, blah, 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 and avoids underruns. You can put headers and data in multiple descriptors or one descriptor. The Ethernet controller provides 3 types of transmit descriptor formats: legacy and extended, and ultra extended, sure. Text. Or dtype. So what is a dtype? I don't see dtype here. So this is the legacy layout. That is what we're using, which means there is no type. This means this is what we set. Checksum offset, command field, status field. So it's like the status field. The status field stores the applicable transmit descriptor, has the field of the transmit field. It's only present in cases where RS is set in the command field. Interesting. So this transmit status won't even show up unless the report status bit is set in the command. That kind of makes sense. And we have transmit status, the special field, which is the user priority, VLAN identifier. Okay, cool. I don't know, it just seems like we should be able to send something. Maybe let's look at an example. Write packet or write raw somehow, somewhere, if we can. E1000 driver cannot receive anything. It actually works fine yesterday. Don't know why it suddenly doesn't work. I can make it work if I use IRQ 0 instead of the interrupt line, but I don't wish to do that. Yeah, that's not great. Where is your code to unmask the IRQ in the interrupt controller? That's during install handler. Ah, hold on.
Are you clearing the or?
So where is it? What am I remembering?
Are you clearing like the interrupt flag before all of this?
So let me look at install handler. So what I'm worried about is that it's possible I'm masking the interrupt because it is a maskable interrupt. But from what I remember, I refactored it so that when you install a handler, see, it doesn't actually unmask the interrupt. So what do I have to do? I have to actually enable the interrupt. These.
Well, if it's not enabled, that explains how I'm not getting it.
That may make sense. Oh, God. Okay. Okay. This interrupt line we now need to enable. Oh my God. Okay. Please give me an interrupt. Give me a triple fault from that interrupt. I don't care, but give me an interrupt.
What does the double fault handler currently do, actually? Does it just crash or does it print something?
It prints like double fault and then just hangs forever, but most of the time it faults in trying to print something. As far as I know, because we get triple faults more often than I've seen a double fault ever. Well, we didn't get any interrupt. As far as I know, we are printing out when we get an interrupt, are we not? Yeah, we're saying interrupt.
It isn't the right file this time, isn't it? Like the interrupt. The handle, I mean. Because I remember we had this entire problem with the interrupt handler being in the wrong C++ file because there are compile flags that need to be set right.
That's true. It's not in the right place technically, but there's nothing here that uses SSE as far as I know. We could try. Because if we put attribute interrupt here, is it going to freak out? It does freak out. So maybe that's the problem. Maybe we have to move this. We have to keep this here. But we have to move this.
Because I remember you mentioning that being a problem like a while back.
Yeah, you can see we also had to do the same thing for the scheduler here. It's a mess.
Oh god, include in the middle of the file.
Yep.
Oh god.
Well, it did compile, so that's a plus.
That's good. Can you hear this, by the way?
I didn't. It was silence.
Okay, this I mean.
Still silence.
Okay, good.
Well, that seems to have went well. Nothing happened. I mean, we're still getting the MAC address, the interrupt line. We flushed the IDT. I'm running out of ideas. Enable interrupt. What does that do? If IRQ is greater than 15, return. What is it? B. Okay, it's less than 15, so that's
Yeah,
that's
B is
wrong.
11.
So if IRQ is less than 8, pick 1 data, otherwise use pick 2 data. And IRQ minus equals 8. So if you don't know, there's basically 2 ports, and they each have 8 IRQs available. So the 16 IRQs, that are supported on x86 are split up between 2 actual I/O ports that determine the, because there's 2 bytes, clearly.
I see.
So basically we read from this port, and then we make sure that the bit is unset, and then we continue on. Is that what this does? Yep.
Yeah,
So this
this
is
unsets the bit.
yes. Do we and unsetting the bit, because this is the like disable interrupt mask, means that it's allowed through. Because to disable an interrupt, we set the bit.
Yeah, that makes sense.
And then we write the port with that value. Presumably this works. Is pick 2 data. It's OXA1, and this is OX21. It's been a while since I did the pick stuff. Yeah. So that's the data, and that's the command. Is that how this... I'm not sure this is correct. See? So what do we have? Pick 1 data or pick 2 data? Ah, I see. So I'm basically picking pick 2 data or pick 1 data, and that's A1 and 2-1 respectively. Sure. May have gotten that backwards. End of interrupt. Are we screwing this up? If IRQ is greater than 8, send pick 2. So end of interrupt. If IRQ is greater than or equal to 8. Whoops. Send to the pick 2 command UI. Otherwise, send to the pick 1 command. It is necessary to issue the command to both pick chips. Initialization. Cascade. What does that mean? What is cascade? Masking looks correct. So to clear the mask, we can clear the bit, and then we don't get... Yeah, okay. So port pick 2 data, IRQ line minus equals 8. In B port, not the bit, and then... Okay. Ugh. Spurious IRQs. No. This is interesting. At this point, I'm not sure why we're not getting it. What is... Okay, hold on. Is there an actual... I don't think there's any actual driver provided here, which is sad. So to send a packet, hey, we can look at what they're doing. He also enables report status. So we set the address, the length, the command, the status to 0. We wrap around in case we need to. That's probably important. We write it back. And then this is a blocking implementation, which waits for status to actually be set properly. Interesting. So I wonder if status isn't 0 or if RS isn't happening and that's causing a problem. We can start copying even more what we have seen before. So, and report status is what we want to do. And we want to set this status to 0.
I mean, yeah, if report status is not set, maybe that's why it's not reporting anything.
It's possible. So we're going to get this thing, by the way. Yeah, basically we can say tail plus equals 1, right? Or just plus plus tail, that's fine. And we want to write that to tail because this is should officially be the last one. And there shouldn't be a race condition because technically we should be locking access to the E1000 while we're using it. So I don't think there can be a race condition in this case when we're interacting with the hardware directly, because we basically would just have to lock the transmit ring buffer as we access and change it.
Yeah, that makes sense.
Okay, no interrupt. I could try adding back the Ethernet checksum at the very end. So I can also modulo the tail. It's going to be, yeah, the count.
Okay, stupid question, but are you sure this code isn't getting called from anywhere?
This code?
Yeah.
I'm sure this is getting called because we printed out earlier and it did have like writing blah blah bytes to buffer blah. We can do that again though. Writing bytes from to descriptor at So we get length, data, descriptor. Cool. Just to make sure that that's happening, tx descriptor count is going to be register tx descriptor length basically, but it's going to be over. So how many descriptors do we have? I don't think we even know. It's actually dynamic. So I think we have to do something like this. And then we can say tail tx desc count.
Well, size of is a static computation, so if it's dynamic, that's not going to work. What do you mean by dynamic?
So the size of this is fixed, but the size of this, we don't have
Mm,
like a preprocessor definition that says there are 32 transmit descriptors,
I see.
because they have this num transmit descriptors definition.
Mm,
Whereas we don't, we have it calculated from like the,
I see.
where is it? From the page count. So we say we want 1 page of transmit descriptors, and then we calculate the maximum count here.
I see.
And then we could probably store this as a member. But yeah, then we write this length. You can see count times size of blah. So to get this count back out, we have to, I mean, technically it's all known at compile time. We could probably just move this to a hashtag define and then use it down there, but it's fine.
Or make it inline context and global.
That's true, like here.
If that's in the header, then yeah. Or is that all in the same file?
This is all in the same file.
Okay. And just as a reminder, inline context for variables of file scope, static context for variables of function scope, and it's a bit complicated, but the reason is basically at file scope it has to be inline, especially if it's in a header, to make sure that definitions get merged. Otherwise, you might get duplicates of the variables in different translation units.
I see.
Inline, and for function scope variables is because it's you want it to be a static variable. That's why. Because a static context variable is guaranteed to be computed at compile time or function scope.
I see. So I'm officially, I turned off the filter on Wireshark, so I'm just seeing everything now. Hey, we got to divide by 0. Wonderful. How'd we do that? What?
Interesting.
Chat is going crazy, by the way. I haven't been able to keep up with it. So this is somehow 0? Oh yeah, that would make sense. We can't read from the txdesklen over size of txdesk register. We have to read from the register, then divide it, as it turns out.
I see. As someone else was saying, per programming at its finest.
That's right. Okay, hopefully we don't get a divide by 0. We have no divide by 0. We
Someone's
have...
asking for like resource recommendations to learn about programming, it seems.
I see. The classics. Well, I don't even know what this is about. So, frame is ignored, coloring rule TCP. It's not a TCP thing. I'm just looking at Wireshark on my other screen and seeing the thousands of packets. So do we actually know?
They can like do not TCP and not UDP or something. That should get rid of most packets.
That's a good idea.
Or just filter by, what are we sending up, right? Just filter by that maybe.
It's Wireshark has frozen because I accidentally clicked on a sort thing.
Oh no.
Yes. It just says sorting protocol and won't respond.
Oh, no. If it's sorting all the traffic it's reported, that's gonna take a bit.
Yeah. I think it's done. It's not coming back. It won't even close. Okay, this is great. Oh, yes, it looks like it's just memory leaking forever. It was just kept increasing its memory usage. So I think I was
Oh.
getting more packets to sort than faster than it could actually, it's receiving packets faster than it could actually do anything.
Interesting. I'm amazed it's willing to sort stuff while it's capturing.
So I hate this. There's a filter for no ARP, but there's not a filter for ARP only.
There should be. Can you just type up?
Well, it doesn't really work.
It worked for me.
I'm still getting UDP and
I
okay,
just put up as a filter.
it has worked. I had to actually press the blue arrow, it turns out.
Yeah, that's the you need to. Yeah, that's the start capturing filter. Oh, the start capturing button.
Yes. So now I'm going to launch LensorOS and hope to God I see something.
I'm pretty sure it's supposed to be like the fin of a shark or something. Because you know it's wire shark.
That would make sense, like sticking out of the water. Nothing showed up in Wireshark. That
Brilliant.
wasn't there already. Oh, okay. Wireshark is once again frozen. Wireshark is very slow.
Interesting. It's not typically really slow in my experience, but I haven't used it that much.
I think it was just while I was capturing, it's slow because there's so many packets and I'm streaming and talking to you and...
I see.
Yeah, because there's already 80,000 packets from like the 10 seconds I was capturing.
I see.
But yeah, there's ARPs here from just like my computer, but there's not ARPs here from
I mean, yeah, if
LensorOS.
it's just capturing ARPs, there's going to be a lot of them.
Yes. So we've figured out we're not sending anything. Brilliant. I've got no ideas on what it could be.
So this, I'd argue, is the annoying part, like the physical layer. Once we get our /low-level link layer, once we've got this figured out, then the rest is going to be easier because at least we'll know how to send and receive packets. And the thing is, if everything below is working, then you can just build the other layers on top. It should just work.
I hate osdev.org so much. I hate parts of it. Whoever wrote this Ethernet I217 page, they shouldn't be allowed to post on this forum ever.
Yeah, I've already ranted at length about the horror that is JXRlib, so whoever wrote that shouldn't be allowed to program anymore, honestly.
You are correct. But this is just, it's so horrid. This page, the way it's put together is so bad. And the reason, because it exists, people aren't going to write their own. Because this already exists, there's already documentation. But the documentation that exists sucks.
Yeah, well, at least there is documentation.
Is this documentation?
I mean, I'm not sure, honestly. Good point.
Is naming...
What does that even do?
It's just... It says you need to make sure to set up the T-control register with the value OB0110000, blah, blah, blah. For more details, reference the manual. You want to go to the manual? It doesn't exist.
Yeah, I know. I saw it.
It's
link is broken.
So annoying. So even if we search in the manual that I found for a different card, but an equivalent one that also follows E1000, I don't know if this is even going to matter because it's not the I217.
Interesting.
We can check it out though. Transmission control. So there's no transmission control register, just to be clear. Okay. Transmit. Okay, That's a thing. Enable. I'm pretty sure we're enabling it. Be pretty embarrassing if we're not. So we're tctl. We read it. We set the enable bit, which is one to the left one, which is exactly what it is. Okay. Reserved PSP, pad short packets, collision threshold, cold, collision distance. So for full duplex, we just go 64 byte time? 40? Because we want to send and receive, right? Retransmit on late collision. No retransmit on underrun. Okay.
Oh god, it's talking about CSMA CD. Oh no. Oh god.
I don't know what any of this means.
This is like not stuff you want to care about. Honestly.
Okie doke. So let's figure out what these crazy bits mean. 0110 in the top 4. Makes no sense because they're reserved.
Fascinating. Well, I mean, again, I don't know this nick too well, but I hope very much that we won't have to deal with like
Is this not 32?
max sub layer stuff because you do not want to get into like CSMA CD and all of that because that gets messy.
There's only
not-
31 here.
Interesting.
Because this is 3, right? And then 4, 8, 16, or 12, 16, 20, 24, 28. There's 28 and 3. We have 31 bits, which
31.
is insanity. Is it 31 up here?
Maybe the MSB is 0.
See the tip G stuff too. So maybe the most significant bit is 0. That's true. But there's only 31 here. It's just weird, isn't it?
Are you sure it's 31?
I'm doubly sure.
Okay.
I mean, we have 4, 8, 12, 16, and we'll remove 16. And then we have 4, 8, 12, 3. There's 15.
See, I suck at counting, so why do I paste this into my IDE and then I mouse over and it shows me how many characters it is, and it is 31, so you're right about that.
Yeah. It's not great. But then they also set the TIPG. So this makes no sense. They're just setting it for no reason because they're reserved. And then what other bits are they magically setting? Let's see. The bottom, so they have the enable bit. They are setting that one. So they do reserved, enabled, reserved, 010. Then they have a 1, 1010. So this is 1 pad short packets, which we do set. Collision threshold is then the next 8 bits, right? Zarias says maybe we are looking at wrong register. We are not.
This is pretty low level stuff.
1, 2, 3, 4, 1, 2, 3, 4. So the bottom 4 bits of collision threshold is set.
Okay, I see. So 15 retries.
And then this, the next 10 bits, right? These, which has the bottom 6 bits set, is the
What is
collision
this?
distance.
That's oh god, oh god.
So what is 6 bits?
6 bits. Is that like the 60? Is that like 63? I think. Yeah.
It's 63. What is the point of setting the collision distance to 63?
Hold on. What does this even do? It specifies the minimum. Okay. That was too fast for me to read, but alright.
Did I switch away?
Yes, you did.
That's my bad.
What is this? Specifies the minimum by times is allowed for purposes message operation. Okay. This is stuff you shouldn't be caring about, candidly. So, isn't there a default or something? I mean, recommended value, it says 40 hex or 2. And,
I mean, we're using the default 40 because I just figured that's the default.
Sure.
But yeah, we can ensure by looking at the default, which is
So for this, by the
OX40.
way, CSMACD, the way that works is, if you're interested, basically, if two things happen to send on the link at the same time, they'll just like corrupt each other's transmission. So you have to somehow make sure that that doesn't happen, and that's what this is about. It's carrier sends multiple access with collision detection. Basically, you start sending data, and you listen to the data that's being sent, and if they're not the same, that means someone else is also sending, and you've detected a collision, and then you basically notify everyone there was a collision, and then you stop sending and wait for a bit and try again, basically. That's how that works, more or less.
Interesting. Okay. Which makes sense because you don't want to stomp on each other. So it's kind of like just built in, making sure packets get there unharmed. So we have control bits 25 through 22, which are these, but I don't think we need to set these. Retransmit on late collision, no retransmit on underrun? Question mark. Is it possible there's well, it says pad short packet, so it should do that automatically. What is the interpacket gap?
Interpacket gap space between packets. We wait a bit between them.
Why is there a timer?
Interesting.
Like, what do we put here?
I mean, it says for apparently 10.
This says should be added.
Below that. No, too far below that. About
Okay.
that's it.
Well, the standard IPG value, the value that should be programmed into IPGT is 10, 6 for the 82544 GCEI. So we program the first 10 bits with decimal 10.
Pretty sure it's decimal 10, yeah.
So this is the TIPG register, which we don't have broken down at all, so we're just going to have to do this by hand. 10. Right? We could technically do our, keep it consistent. So 10 to the left 0 and OB. Right?
I suppose, yeah.
And then
I think it is.
What does this say? IPGR1 should be 2/3 of IPGR2.
Naturally.
IPGR2 is 6. Okay, so IPGR2 is to the left 20, and it's also 10 bits, right? And then we want to write 6. And for IPGR1, 10 bytes, it is 2/3 of IPGR2, which means it's going to be 4. Yeah? Cool. I think so. I don't know what any of this does. Just no clue. I've got Wireshark capturing. I've got 6 ARPs, which there was last time.
Oh.
Well, I waited a long time just in case it was taking some time. I don't see anything in Wireshark that has to do.
God. I'm looking at like CSMACD and computer net because I'm getting flashbacks to studying for my networking exam. Oh God.
Writing 42 bytes from blah to descriptor at blah. Is it seriously not? What is happening? Okay. So that was this. This happened. Writing blah bytes from blah to descriptor at blah. That's it, huh? No interrupt. No transmission. LensorOS is basically me in today's stream. Just need to study how does UTP actually works. UDP? We did go over that earlier, but yeah.
UDP is a fairly simple one.
LensorOS says TCP. Ah, yeah.
TCP is a bit harder.
That's a different one.
Well, with sequence numbers and all the TCP options and sliding window and so on.
So do I have to read this and then add 6? Am I crazy? Because in order to calculate the actual value, a value of 6 should be added to the IPGR2 value, as 6 MAC clocks are used by the Mac for synchronization.
Maybe you need to. Interesting.
Oh, okay. No, I'm understanding now. So when we store the value 6, right? It says total IPG delay of 12 cycles. So to get the amount of cycles that it's actually delaying, because the internals of the card, there's 6 MAC clocks that are used for synchronization and internal engines. So these 6 are basically just implicit, but whatever we program here is still going to be whatever we program here. It is confusing, very confusingly worded. Okay. IPGR. I've got nothing. We're doing everything as far as I can tell. Also, I don't understand this number at all. We know that _A, right? That's 10. But then these are all offset by 10 bits. Offset by 10 bits, so it's hard to see. And then we have some weirdness happening when we enable interrupts. So let's look at how we enable interrupts. We are writing to register IMASC, not OX1F6 DC. But we're enabling the timer interrupt and the FIFO overrun and the sequence error and the link status change. So I don't think anything here is actually happening. Are we missing? We're not using MDIO, so that shouldn't matter, right? And then we have RxTX descriptor. TXQ empty. TX descriptor written back. We're just going to enable all the interrupts, not the recommended ones, all of them. Jamil Faluda says, "Damn, I wish I could understand this stuff." You can. I promise. There's nothing different between you and somebody else that understands this stuff other than the amount of time they've tried. Molly the Man says, "Read books." Well, that's one way to do it. This is a good sign.
Oh,
I think we've done it. I think we have an interrupt. I think the interrupt causes a general protection fault, but I think we're getting an interrupt. PogChamp. So you would think we'd be able to print something, right?
Mhm.
And we are calling interrupt. Yeah, here's the handler. Here's the... Yeah, we don't need to do that anymore. So we should be seeing this at least, even if there's an error here. Which is interesting. There's been an interrupt. What if I don't handle interrupt? It's never time to ask ChatGPT. It's never time. Especially with a complex thing such as this, which will just cause horribleness. So this looks like the instruction address of a user space program that is causing a general protection fault, which is not ideal. And it also doesn't make sense how what I'm changing changes user space at all. So that's a little annoying. Let me just check that what I passed to enable interrupt. Like, where are these actually defined? Perfect. So these are just numbers, yeah. And we're on peripheral 1. So setting 1 to the left 10. Yeah, everything should be fine. Have I enabled the cascaded pick? That'd be pretty silly if I haven't enabled that. Okay, I've enabled the cascaded pick. We're good there. I'm not that silly. We have printers, RTC, and then peripheral. And we're on the 10th peripheral. I am not even sure what's causing the general protection fault at this point, to be honest with you.
Perhaps it's you deleting the buffer.
Maybe. I don't know how that would cause a GPF from user space.
I mean, hmm.
Zarya says, I feel like networks thingies are static enough for it, though. That's an interesting feeling you have. Well, let me start up Wireshark and see if we're actually getting an ARP. Because if we're actually transmitting something, that'd be sweet. It at least shows progress. There's nothing that showed up. It's blank. Ugh. I've got no ideas.
I mean, the user's space code that it runs is the init process, right?
Yeah. I mean, it was running. So it's just the things I've done since then have broken it somehow. So what if we just set this up before enabling interrupts now? Technically, we could miss it, but we'll see. I just want to see what happens, really. Because it's possible that the interrupt will be queued. It depends on the implementation. I didn't see nothing. Interesting. Interesting. Yeah, I truthfully have no clue. I could try adding back the footer. Don't think it's good. I don't think it's gonna matter, but I could try. And then after that, I gotta go. By the way, thank you so much for that awesome networking in educational segment. I don't even know what to call it. It was like a TED Talk. Oh God.
I love the periodic interrupts at float huts.
Some sort of float.
Because we still don't have floats in the kernel, do we?
Yeah, we don't. We could, but we don't.
I see how it is.
Basically, it's just you'd have to be really careful in syscalls and anything that's called from a syscall. Because you'd have to manually save and restore the floating point context in a syscall. I've got no ideas for what to do now. So, that's that. Yeah, unless you have any ideas.
I'm not sure. I don't think I do.
So we're not even getting an interrupt? Okay, here's an interesting thought. What if it's not being remapped by the PIC and it's bypassing the PIC and just triggering the interrupt line on the CPU? What's the interrupt line for a general protection fault? Is this in K-Stage 1? It's OXOD. Well, it's not the same. Okay.
Hmm.
So we're probably getting a general protection fault. So what if I just flush the thing? I know we already do this after this because we have to set up the scheduler. In doing so, we flush the IDT. That'd be horrible if we just weren't flushing the IDT.
Hmm.
I mean, it wouldn't be horrible because it would be about to work and that'd be cool, but... Well, I got nothing in Wireshark and nothing here, as you can tell, as well. So that went well. So what exactly did I do that caused us to fail? Because I'm pretty sure with these, timer, overrun, min threshold, sequence error, and LSC. I guess I also did small packet detection. And I think every time we read from ICR, it gets set to 0. No? Hmm. There we go. Jesus.
Hmm.
All register bits are cleared upon read. Okay. Writing a 1B to any bit in the register also clears that bit. Interesting. Writing a 0-bit tiny bit has no effect. Well, it ran. So it has something to do with the interrupts that were enabled. Which
Interesting.
doesn't make sense to me because we're not getting an interrupt. So kind of confusing as to how it's causing a general protection fault just to enable these interrupts.
Also, by the way, I think I'm gonna stop sharing my screen for now.
That's probably doable. I totally forgot that was happening. That means when I switch back to this window view, I'm going to now have to do max. And I can resize things. Yay. Isn't this fun? Beautiful stuff. Just reorganizing the stream. Don't worry about it. So these are all what? The interrupt bit that was set. Okay. So in handle interrupt, we read the ICR register, assuming we even ever get here. But there's nothing that we're actually doing. We're doing this for a link status change, but we would hopefully at least see something. So just, yeah. We already read ICR here as well, so I don't know if we need to do this at the end. In any case, seems like that would work. Ooh, going back to the manual. What does it say? Transmit descriptors. So is there a minimum length? A buffer as short as 1 byte is allowed. The total length of the packet before padding and CRC insertion must be at least 48 bytes. Are we writing 48 bytes? Is that what this is? I don't know what this means, so I'm just going to copy it. Sure. I'm not doing a mem copy after this. I've already done my mem copy. So length now just refers to what I'm storing here. Then we're going to say making packet larger. Sure.
Oh.
It's not a packet. Making thing larger. Okay. Hello? Did I did that? I really did that?
Welcome back.
Hello. Welcome back. You made it. Was I gone?
You were gone.
I was gone. Where did I go?
I don't know, you just disappeared.
Hopefully I didn't. I've been talking.
I mean, just now.
Oh, okay. I have no clue. There's so much going on technically right now. Well, we made it larger. It didn't help. Nothing happened. I guess I didn't have Wireshark open. So the idea is that there's a minimum size, and we were too little because we were sending 46 bytes and not 48, and it just wasn't listening. But yeah, it doesn't look to be the case because there are no ARP requests on the network at the moment.
By the way, you're not sharing your screen anymore, but I can also just look at the screen.
Oh, did I change that?
Well, you were gone. That sort of disconnects you typically.
Interesting. I don't know how this works. I don't know what I did. Okay, it should be back.
There we go.
Hey, PogChamp. Okay, there's a more lenient filter in Wireshark where it just checks the type of the Ethernet header, not like whether or not it's a recognized ARP or anything. So if the type of the header is 0806, we should see it. It's capturing. We start on 0. Nothing happens. Phantasmal. Well, it was too small, but that doesn't seem to have helped us. So, just ask ChatGPT to fix it. Yeah, that'll work great. Humans have wrote horrible documentation for
I
this,
mean, let's be honest, I don't think ChatGPT can produce anything that's any worse than this.
right? We're just writing 0 to a bunch of things here. Kind of weird. IRQ 0. So when they register the interrupt, why are they doing that? Oh God. So when we install a handler, we start at offset. Okay. So the entry offset is implicitly offset. Don't have to worry about that. Okay. Interesting. There's not really a lot of glue in here. What is bus mastering? Enable bus mastering. What is that? PCI config header. Okay. I don't see anything there. What is bus mastering? It's a bit in the command register of the PCI device structure. Okay. So when do we do this? Enable bus mastering. I've never even heard of this. This is the constructor, so it happens very early. Jeez, okay. So it's like, let's say in here, well, it's even before we initialize things. So let's say we configure the device. So PCI header dot command. Do I just set this bit? This is MMIO, so it should listen. Cannot generate PCI accesses. Okay. Enable bus mastering, I guess. I don't even, why? Why do we do what we are doing? And then we say EEPROM exists false. I don't get that one. That's a little confusing. Also, he misspelled it. EEPROM.
EEPROM.
I wasn't listening on Wireshark.
That's a classic.
We have writing raw, making larger, and then no response. I'm going to start up Wireshark. And hopefully we capture this transmission. Now that it's a bus master. Nothing in Wireshark. Hmm. So we can't, like, there's no interrupts. Interrupt disable. So if set to 1, it's disabled. So we need to set interrupt disabled to 0. That's bit 10. Okie doke, we're gonna try it. And equals not 1 to the left, 10. Still listening on Wireshark. Ao Nitgo Guano says Domo Terminato Roboto Arigato, motherfucker. I didn't get anything from. I did get 6 ARPs, but they're all from my actual computer. And none of them have the proper thing set up. So, it doesn't work. We've enabled bus mastering. Ensure interrupts are not disabled. Right, so you can set it to disable, but we should set these both to 1, sure, whatever. Status register header type, blah, blah, blah. So it looks like to perform DMA to main memory, they need to bus master. Is that right? Middle Cloud, hi, what's up? We love you, Middle Cloud. It's so cool to see you here. So basically, bus mastering enables that. Cool. We've enabled it. Cool. Capabilities list. Oh my. Well, I have no clue. Is there an example? Like, can we look at free BSD or something? This isn't what I want. I want to go here. Okay. Middle Cloud says searching for work. I see.
I mean, the first link earlier was the Linux driver, apparently, so
It was?
if you go back a bit. Still back. Yeah.
Pog. There's more than one file, for fuck's sakes. This, oh no.
Look at the scroll bar.
I've realized.
5,636 lines, apparently.
don't like
Fascinating.
this. I don't think I'm going to learn anything from that. So I'm going to go net here. Net, hello? Am I crazy?
You can use GitHub search to search for that, perhaps.
That's true. I swear I was just looking at it, but we'll see what happens. Sysdev. Naturally. Okay. Oh, God. So this is a lot of like function pointers and driver stuff. Where's the actual init? So this is how to reset the hardware, apparently. So it masks. Oh no. Here's a thought. An interrupt mask, you're supposed to clear the bits. Right? This isn't doing that.
So we're doing it the wrong way around, is what you're saying.
I think so. Where we're disabling all of these. Which is why, I don't know. I don't know why. So let's get U32 interrupt mask. We're going to say interrupt mask equals all ones. Right? That's a byte. That's 4 bytes, all ones. And then we actually want to AND equals with the not of all of this. Right? So we want to AND it with that. I guess we don't even need to read it if we're just going to do this. Middle Cloud says, that's the reason why I resisted from the previous job was not what I wanted at all. They migrated from agile to waterfall model. That's going to go well. Middle Cloud says, which packages you are looking to cut, what layer? Well, we're currently just doing a very simple ARP. We're writing a very basic ARP, which is an address resolution, right? And we're just giving this dummy address to try and find something meaningful. Middle Cloud says layer 2 then. Maybe? I don't know the numbers. Kiwimu attempted to allocate like 1 billion bytes.
Layer 2 is the link layer, so yeah, it's layer 2.
I see. That makes sense. QEMU just crashed because it tried to allocate a million or a billion bytes.
For a second.
I don't really get it. The paging file is too small for the... Why would you try and allocate... QEMU, why?
You were gone for a second, by the way.
What does that mean?
You left the call and now you're back.
Okay. I'm not doing that.
Your connection is doing that apparently.
Yes. It's probably Wireshark.
Could be. Also, maybe you didn't hear my answer, but data link layer is layer 2.
Oh, okay, okay. That makes sense. Middle Cloud says search for OSI model.
Yeah, we just had like an I don't know how long introduction to that earlier.
Yeah. That was the beginning of this stream. Well, I don't get it. We just get a general protection fault. Cool. That's not really helpful. Can we disable all the interrupts? How neat Quano says Wireshark is tapping everything, including you. Maybe. Yeah, I don't think I'm going to get this working today. I don't understand it. Because how does masking off all the interrupts become a problem? Is it not? It's IMS, isn't it? Okay. An interrupt is enabled if its corresponding mask bit is set to 1. And disabled if its mask bit is set to 0. So it wasn't backwards. We had it right the whole time. Classic. So we're not writing bit 5. Software uses this register to disable an interrupt. Weird. So there's an entire register that just lets you write to it a 1 in order to disable these. It's kind of confusing. Then let's look at transmit control. Flow control, receive, flow control, receive descriptor. Okay, that's not going to help us. Well, they set them to all 1, so they enable all of the interrupts. Or they somehow have this special case, and this is backwards, but they enable all the interrupts, whether they know it or not. They write 0 into receive control and write pad short packets into transmit. And then they flush the writes, which apparently they don't do, question mark. Read from the control register. And then, just write the reset bit. Okay. Wait for some time. Disable hardware ARPs on ASF enabled adapters. I don't know what that means. Mancy. We again write all ones to the IMC register, which we have done before. Ah, that's not the interrupt masks. That's the interrupt mask clear. I'm getting it now. So this disables all the interrupts. Then it reads ICR to make sure any pending interrupts are done. So maybe let's try this IMC type of thing to disable all the interrupts first. Because maybe we're getting like, I don't even know. I have no clue. Middle Cloud says Wireshark is good for above level 3. Yeah. It's definitely more tuned for like UDP, TCP, transport layer stuff. And above.
And to be fair, there isn't really much to do when it comes to ARP. Like it's not a complicated protocol, so there isn't really much you can do with it.
Right. It says making larger. Then nothing else. So presumably they get the LEDs is the first thing they set up in FreeBSD.
Yes, that's a good idea. We should do that too, so that we can see if it works. We could just need to look at the LEDs and we'll see if it's working, right?
Easy. Set up the receive address. Zero out the multicast table. Setup link and Flint. What is setup link? E1000 setup link. What is that? Search for that. Why don't you search for this? No? Okay. This thing? Symbol view? It's not going to search for it. Okay. Well, that's the only one in the file. Naturally. Excuse me? Oh my god. Where's it gonna be? Is it an E1000 base? API. Okay, we're searching. We're gonna resort to GitHub search. That's how desperate we are.
GitHub search can be pretty useful. It's like the only way I managed to like figure out how to use OpenJPEG. More or less, it's just to search for other people using it. That and stepping through it. Because the documentation was pretty non-existent.
I don't know what any of this does. It's very confusing. So we don't enable flow control, so we shouldn't have to do this. It just says it doesn't hurt to do this, so they do it anyway. Call the necessary media type subroutine to configure the link. What does this even mean? What? check reset block. This is all the physical layer stuff. I don't know why we would need to do this. I don't really see anything. That's exactly what I need to do. I've got no ideas. Do you have any idea why it's not working?
Not particularly.
Fantastic. Well, I've done a lot. I wrote a bunch of code, and there's no proof that it works at all. I could hope and commit it anyways. I could make a branch. Well, do you feel interested in debugging this at all?
I don't think I have the time for that, unfortunately.
That is okay. I wouldn't expect you to. That was the expected answer. So that means I should probably just push this all and not really care.
Sure.
Or not push it.
We'll put it in a separate branch or something.
Yeah, because I don't think like I need to get it to you. And so you can change it. I just need to fix it. Well, that's that. Middle Cloud says maybe TCP dump, but I don't know what that is. And we don't have like TCP anything.
I don't think that's gonna help us. It's
Not
like
at all, yeah.
an alternative to Wireshark, if I recall correctly. So, but Wireshark works just fine.
And it
You
looks
don't
like
need T-Shark or something else.
and it only works with
And-
IP packets.
Yeah, I'm sure. I'm not terribly familiar with TCP dump, but Wireshark works just fine.
Yes. Well, I have no clue. I've read the manual very extensively, and I'm not sure what I'm missing. Has nothing to do with receiving, so we should just be able to transmit either way, right? But it is not happy about that. Yeah, I'm not sure. It is very odd. Is there another iMask? Do we have physical interrupt? We have TX written back, low threshold, Q empty. What if I try and enable written back? And then I really gotta go. Middle Cloud says TCP dump is from layer 2 and you can debug from the host machine. Well, we caused a general protection fault at some crazy address. That's cool, I guess. I'm really not understanding what's happening right now.
Also, TCP dump doesn't work on Windows, if I recall correctly. And
That might be a
again,
problem.
Wireshark works just fine.
It definitely does.
Wireshark isn't the problem. I'm pretty sure our ARP code is the problem, or the networking code in general.
For sure.
Because you were getting ARP packets in Wireshark earlier, weren't you?
Yep.
Just
all
not ARP packet.
Yeah, just from my host machine. Well, yeah, I don't think I'm going to do anything drastic. I'm just going to, I guess, work on this tomorrow if I can. We will see. Anyways, I'm going to be winding down the stream because I got nothing left. I'm switching it to goodbye. Molly the team says, can we ping Google now? Not quite. It'll probably be another 2 years before that.
That's gonna take a lot. I mean, with ICMP, if I don't know if Google responds to ICMP, but I mean, again, once we have a working link layer, the rest is comparatively straightforward, I'd say. Maybe not simple, but straightforward, and you just need to implement the protocol, and then you can actually debug stuff because you will see the packets being sent.
Yep.
So the hardest part then is probably going to be TCP everything before that isn't that complicated. It's just filling in headers and sending packets.
Pretty much. The sending packets part tends to be pretty complicated, I've found out. Well, we'll get there. I really can't believe there's not like a minimal, here's what to do to set it up documentation. Because I followed all that. All this is at the beginning of the manual and says, if you want to receive, you have to initialize it in this way. You go through and do all these bullet points. And I did that, and I did that for transmit as well. If that makes sense. Pretty much always right. It does 10. Now getting it. But yeah, I'm really not sure what to do at this point. I guess I'll just have to work on it. I don't know if I should read this again or what. The tail pointer points one entry beyond the last hardware-owned descriptor. Transmission continues up to the descriptor where head equals tail, at which point the queue is empty. Circular buffer, base, head, tail, base plus size, blah, blah, blah. This is when we read the tail and then add it to our pointer. Indicated by the hardware head register. Hardware tail register points one beyond the last valid descriptor. Software can determine if a packet has been sent by setting the RS bit in the transmit descriptor command field. Checking the descriptor done bit in memory eliminates a potential race condition. All descriptor data is written to the I/O bus prior to incrementing head register, but a read of the head register could pass the data right into them. So when we're finished with transmitting, we should get a transmit queue empty, which we don't have enabled. But if I do enable it, what happens? Molly the man says, and your friend, he is smart. I agree. Sarade is very smart. Anyone who can keep not only all of that nonsense with layers and networking, but also the nonsense of all the image processing libraries and
I'm not sure which one is worse, kind of like.
So if we don't enable this interrupt, does it work? It does. But so if we enable this interrupt, we get a crash, which means that this interrupt has to be happening, or somehow setting this is causing an error. Just enabling the interrupt is causing a general protection fault. Not like the interrupt is firing and then that causes a fault. It's just somehow setting that makes something else fault. That seems to be the case. Then the instruction address is the entry point to the user space process, which doesn't make any sense how an interrupt causes this. Copying virtual to physical. Copying pages from virtual data to physical scripter address. I just want to see if this happens to be in the same exact range somehow of this. Because then that might make a little bit of sense if somehow in the kernel we've replaced this physical memory. But we shouldn't have. What was I looking at? It's supposed to print something out when I'm writing, which appears to never have happened. Okie doke. So this never even got printed. Because what? I don't get this. I don't get this at all. Oh well. I'll get it at some point. With that being said, I have nothing left. I don't know what else to try, and I've got to go soon, so it's a good time. Thank everybody so much for watching. I had a great time today. I didn't expect to stream this long, because my voice isn't particularly strong. But I made it. I made it. I didn't lose my voice, so that's a win. If you are not already, be sure to check out the link to the Discord down below to get a exclusive access to announcements every single time I go live. And you can also just be a buddy. We like buddies, and there's lots of buddies here. And I know you can be one. So yeah. Oh, also you guys can't see this. My bad. Come join the Discord. You get announcements. It's fun. We have a ton of fun. It's a great time. And then there's the YouTube, which has all my VODs, my previous broadcasts, all of them, all 8 days or whatever of the compiler. That's all on there. This video will be on there very soon, and you can check out the beginning to find the, oh man, the description of the network stack. Tomato543X, thank you so much for the follow. Same with RWXCOC and Jamil Faluda and Gadutis and Het Tanis. and nomadic for life. Thank you. I don't know why I said it for life instead of nomadic for life, but I'm good at that. Don't worry. Is there anything you would like to plug, good Suraid?
Not a particular thing.
Okay, I'll do it for you. Go to the description and there's a Patreon link. Go support this man. He's smart and he's awesome and he makes educational content. Not directly, but through everybody else. By being an amazing help and just an overall educated person who can eloquently describe these complex topics. Middle Cloud, by the way, says, bye-bye, good night, see you later. Bye, Middle Cloud. Middle Cloud is our most recent contributor, and we really like Middle Cloud, so give them some love before they get out of here. And Molly the Man says, let him make a Twitch account. No, he's not allowed. I won't let him.
I have a Twitch account, so...
Exactly. No, you're not allowed. Just don't you understand? But yeah, go check out what Suraid does. He's really cool, and it's worth it. And yeah, there's also all sorts of links down below, I'm sure, to the manual I was using today. And yeah. Oh, one thing I did want to ask: do you still have your Excalidraw open?
I've closed it, but I can reopen it. It's in my browser. Why?
Is there like a way to save a permanent link to that?
Yes, I can export it.
That'd be
export
sweet.
it as an image.
Okay, then I can put that in the description and people can see that mind map of notes.
I just need to open the right browser again because I have like 5 of them. I believe this one is the one from today. Hold on.
Pog.
Let's see. Is this the one? I think it is. Yeah. Okay. Let's see. How do I export this again? Here, export. As like a PNG. Sure, the canvas is too big, so I need to export it as an SVG. Because
That'll be
Excalibur
perfect.
can't handle exporting it as a PNG, apparently. So
It's,
hold on.
you're asking for like a 16,000 by 16,000 PNG.
What did it say, though? Excuse me? Rome. Oh, good God. Hold on. Apparently, I can make a link. So hold on. Export a link. Let's see if we can handle this. Okay. Sure. Apparently, so hold
Pog.
on. Where is well, let me see if this works. Let's see. Sure, that seems to have worked. Just a disclaimer, because the canvas got too big, I think that's the main reason my handwriting got progressively worse towards the end. So if you can read that, then I'm. So
I think
anyway,
it would mainly awesome. It didn't work. Can you send it in the Discord?
Twitch broke it. Yeah. Hold
Yeah.
I'm gonna.
Classic Twitch.
Hold on. How about this?
But yeah, I think people would mainly use it as a way to follow along. So I think that'd be perfect. Because I feel like
you can put that in the description or something, or if you're if someone's actually interested in learning more about networking, the book on networking is Computer Networks by Tanenbaum.
There you go. You got a book recommendation. I'll also put that in the description if I remember it. Tanenbaum. Molly the Man says this is cool. Awesome. I'm glad you think so. We are good. I'm at the time where I've done everything I need. And we don't have much left. Any closing remarks?
None that I can think of, other than here's the name of the book.
Beautiful. Beautiful, beautiful. That'll help a lot. For me to not immediately forget it. But yeah, thank you everybody so much for watching. I hope you enjoyed. I hope you learned something most of all in this incredible stream where we learned all about networking at the lowest level. Ooh. So yeah, thanks everybody for watching. We'll see you next time. Subscribe to the YouTube, click the follow button. Go press all the buttons in a row right now. All right, goodbye.
Ta-da.